Chemistry. All topics and notes. Matter. 1. Solid. A solid is a state of matter characterized by a definite shape and volume. The particles in a solid are tightly packed together and vibrate in fixed positions. They have a strong intermolecular force of attraction. Examples of solids include ice, wood, and metal. 2. Liquid. A liquid is a state of matter that has a definite volume but takes the shape of its container. The particles in a liquid are close together but have more freedom to move compared to a solid. They can slide past each other, allowing the liquid to flow. Examples of liquids include water, oil, and milk. 3. Gas. A gas is a state of matter that has neither a definite shape nor volume. The particles in a gas are widely spaced apart and move freely in all directions. They have weak intermolecular forces and are constantly in motion. Gases can expand to fill their container. Examples of gases include oxygen, nitrogen, and helium. These are the basic states of matter, but there are other states as well, such as plasma and Bose-Einstein condensate, which occur under specific conditions of temperature and pressure. The particulate theory of matter is based on the idea that matter is composed of tiny, indivisible particles called atoms or molecules. The evidence supporting this theory comes from several scientific experiments and observations. Here are some explanations of how the evidence supports the particulate theory of matter. 1. Brownian motion. In 1827, the botanist Robert Brown observed that pollen grains suspended in water showed irregular, random motion. This phenomenon, known as Brownian motion, was later explained by Albert Einstein in 1905. The motion is caused by the constant collisions of water molecules with the particles. This observation suggests that matter is made up of small particles in constant motion, supporting the particulate nature of matter. 2. Diffusion. Diffusion is the process by which particles spread out from an area of high concentration to an area of low concentration. When a drop of dye is placed in a glass of water, the dye particles gradually spread throughout the water. This behavior can be explained by the movement of individual particles, indicating that matter is composed of discrete units that can move independently. 3. Brownian motion and diffusion relationship. The observation of Brownian motion and diffusion are interconnected. Brownian motion is the result of the random collisions between particles, and diffusion occurs due to the net movement of particles from regions of higher concentration to regions of lower concentration. Both phenomena support the idea that matter consists of individual particles that are in constant motion. 4. States of matter. The behavior of matter in different states also provides evidence for the particulate nature of matter. In solids, the particles are tightly packed and have a fixed arrangement, explaining their definite shape. In liquids, the particles are still closely packed but can move past each other, allowing the liquid to flow and take the shape of its container. In gases, the particles are widely spaced and move freely, explaining their ability to expand and fill their container. The distinct behaviors of these states can be explained by the behavior of individual particles. 5. Atomic and molecular spectroscopy. The study of atomic and molecular spectra provides direct evidence for the existence of discrete particles. Spectroscopy involves the analysis of the interaction between matter and electromagnetic radiation. Different elements and compounds produce unique spectra, which can be explained by the specific arrangement and energy levels of their constituent particles. This supports the idea that matter is composed of individual atoms and molecules. These pieces of evidence collectively support the particulate theory of matter, providing a foundation for our understanding of the physical properties and behavior of different substances. Here's a distinction among the three states of matter: solid, liquid, and gas. 1. Solid. Definite shape. Solids have a fixed shape and volume. The particles in a solid are tightly packed and arranged in a regular pattern. Strong intermolecular forces. The intermolecular forces between particles in a solid are strong, causing them to vibrate in fixed positions. Incompressibility. Solids are generally incompressible, meaning they cannot be easily compressed or squeezed into smaller volumes. Examples of solids include ice, wood, metal, and rock. 2. Liquid. Indefinite shape, definite volume. Liquids take the shape of their container, but they have a definite volume. They can flow and be poured. Weaker intermolecular forces. The intermolecular forces in liquids are weaker than in solids, allowing particles to move more freely. Moderate compressibility. Liquids are generally less compressible than gases but more compressible than solids. Examples of liquids include water, oil, milk, and alcohol. 3. Gas. Indefinite shape, indefinite volume. Gases have neither a definite shape nor a definite volume. They expand to fill the container they are in. Weak intermolecular forces. The intermolecular forces in gases are very weak, allowing the particles to move independently and rapidly. High compressibility. Gases are highly compressible because the particles are far apart, providing space for compression. Examples of gases include oxygen, nitrogen, helium, and carbon dioxide. These distinctions highlight the differences in the arrangement, motion, and physical properties of particles in each state of matter. It's important to note that matter can undergo phase changes, such as melting, boiling, or condensation, which involve transitions between these states. The changes between the three states of matter, solid, liquid, and gas, involve variations in the energy and arrangement of particles. Here's an explanation of these changes. 1. Solid to liquid, melting. Energy increase. When a solid is heated, energy is added to the particles. This additional energy causes the particles to vibrate more vigorously, overcoming the intermolecular forces that hold them in a fixed position. Arrangement of particles. In a solid, the particles are closely packed and arranged in a regular pattern. As the solid is heated and melts, the particles gain enough energy to break free from their fixed positions and move more freely. Result: the solid undergoes a phase change and transforms into a liquid. The particles in the liquid state have more freedom of movement, but they are still relatively close together. 2. Liquid to gas, vaporization, evaporation. Energy increase. When a liquid is heated, the energy supplied to the particles increases. This added energy causes the particles to move faster and gain sufficient energy to overcome the intermolecular forces that bind them together. Arrangement of particles. In a liquid, the particles are still close together but are not fixed in position. As the liquid is further heated, the increased energy disrupts the intermolecular forces, causing the particles to move more freely and become more spaced apart. Result: the liquid undergoes a phase change and turns into a gas. The particles in the gaseous state have high energy and are widely dispersed. 3. Gas to liquid, condensation. Energy decrease. When a gas is cooled, energy is removed from the particles. As the temperature decreases, the particles lose kinetic energy, causing them to slow down. Arrangement of particles. In a gas, the particles are widely dispersed and move independently. As the gas is cooled, the decreased energy allows the intermolecular forces to become significant, and the particles start to come closer together. Result: the gas undergoes a phase change and condenses into a liquid. The particles in the liquid state have less energy and are closer together compared to the gas state. 4. Liquid to solid, freezing, solidification. Energy decrease. When a liquid is cooled, energy is extracted from the particles, causing them to lose kinetic energy and slow down. Arrangement of particles. In a liquid, the particles are relatively close together but move freely. As the liquid is cooled further, the decrease in energy allows the intermolecular forces to become dominant, and the particles arrange themselves into a more ordered, fixed pattern. Result: the liquid undergoes a phase change and solidifies into a solid. The particles in the solid state have minimal energy and are tightly packed in a rigid structure. These explanations illustrate how changes in energy and the arrangement of particles lead to transitions between the different states of matter. Heating or cooling affects the energy levels of the particles, enabling them to break free or come closer together, resulting in the observed phase changes. Here's an explanation of mixtures and separations. 2. Mixtures. A mixture is a combination of two or more substances that are physically combined. Each component of a mixture retains its own properties and can be separated from the mixture using physical methods. Mixtures can be classified into two types. A. Homogeneous mixtures. In a homogeneous mixture, the components are evenly distributed throughout the mixture, resulting in a uniform composition. The particles are not easily distinguishable. Examples include salt water, air, and sugar dissolved in water. B. Heterogeneous mixtures. In a heterogeneous mixture, the components are not uniformly distributed and can be visually identified. The particles are distinguishable and may settle or separate over time. Examples include a mixture of sand and water, oil and vinegar, and a salad with various ingredients. 3. Separations. Separation techniques are used to isolate or extract the components of a mixture. The choice of separation method depends on the nature of the mixture and the properties of its components. Here are some common separation methods. A. Filtration. Filtration is used to separate solid particles from a liquid or gas. It involves passing the mixture through a filter medium, such as a paper or mesh, that allows the liquid or gas to pass through while retaining the solid particles. B. Distillation. Distillation is a technique used to separate a mixture of liquids based on differences in boiling points. The mixture is heated, and the component with the lower boiling point vaporizes first. The vapor is then condensed and collected, resulting in the separation of the components. C. Evaporation. Evaporation is used to separate a dissolved solid from a liquid. The mixture is heated, causing the liquid to evaporate, leaving behind the solid residue. D. Centrifugation. Centrifugation is a method used to separate solid particles or denser liquids from a mixture by rotating it rapidly. The centrifugal force causes the denser components to settle at the bottom while the lighter components remain in the supernatant. E. Chromatography. Chromatography is a technique used to separate the components of a mixture based on their differential affinities to a stationary phase and a mobile phase. The components travel at different rates through the stationary phase, leading to their separation. F. Magnetic separation. Magnetic separation is employed to separate magnetic materials from a mixture using a magnetic field. The magnetic component is attracted to a magnet, allowing for its separation from the non-magnetic components. These separation methods are just a few examples, and there are several other techniques used depending on the specific properties of the mixture and its components. Here's a distinction between pure substances and mixtures. Pure substances. A pure substance is a type of matter that has a definite and constant composition throughout. It consists of only one type of particle, either atoms or molecules, and cannot be separated into simpler components by physical means. Pure substances can be further classified into two categories. 1. Elements. Elements are pure substances that are composed of only one type of atom. Each element has its own unique set of physical and chemical properties. Examples of elements include oxygen, gold, and hydrogen. 2. Compounds. Compounds are pure substances made up of two or more different types of atoms chemically bonded together in fixed ratios. Compounds have their own distinct properties, different from the elements they are composed of. Examples of compounds include water, H2O, sodium chloride, NaCl, and carbon dioxide, CO2. Characteristics of pure substances. Consistent composition. Pure substances have a fixed composition with a specific ratio of elements or atoms. Fixed melting and boiling points. Pure substances have specific melting and boiling points at which they change state. Unique physical and chemical properties. Pure substances exhibit characteristic physical and chemical properties that are specific to the substance. Mixtures. A mixture is a combination of two or more substances that are physically combined and can be separated by physical means. Unlike pure substances, mixtures do not have a fixed composition and can vary in their proportions. Mixtures can be further classified into two types. 1. Homogeneous mixtures. Homogeneous mixtures are uniform throughout, with the components evenly distributed. They have the same composition and properties in every part of the mixture. Examples include salt water, air, and sugar dissolved in water. 2. Heterogeneous mixtures. Heterogeneous mixtures have non-uniform compositions, with visible differences or variations in their components. The components of a heterogeneous mixture can be distinguished and may settle or separate over time. Examples include a mixture of sand and water, oil and vinegar, and a salad with various ingredients. Characteristics of mixtures. Variable composition. Mixtures can have varying proportions of their components, and the composition can be adjusted. No fixed melting or boiling points. Mixtures do not have specific melting or boiling points since they are composed of multiple substances. Components retain their individual properties. The components of a mixture retain their own properties and can be separated using physical methods. In summary, pure substances are composed of only one type of particle, either elements or compounds, and have a constant composition, while mixtures are combinations of two or more substances that can vary in composition and can be separated physically. Here's a distinction between solutions, suspensions, and colloids. 1. Solutions. Solutions are homogeneous mixtures where the solute, substance being dissolved, is uniformly dispersed in the solvent, substance doing the dissolving. The solute particles are typically very small and are molecular or ionic in nature. Solutions do not separate upon standing and do not scatter light. Here are some key characteristics. Particle size. The solute particles in solutions are tiny and often cannot be seen with the naked eye. They are usually smaller than 1 nanometer in diameter. Homogeneity. Solutions are uniformly mixed, appearing the same throughout, with no visible separation of solute particles. Transparency. Solutions are usually transparent and do not scatter light. Examples: salt water, sodium chloride dissolved in water, sugar dissolved in tea, and air, a mixture of gases. 2. Suspensions. Suspensions are heterogeneous mixtures in which solid particles are dispersed in a liquid or gas but are not dissolved. The solid particles are typically larger and can settle or separate upon standing. Suspensions can scatter light, resulting in a cloudy or opaque appearance. Here are some key characteristics. Particle size. Suspensions contain larger particles, often visible to the naked eye. The particles can range from a few micrometers to several millimeters in size. Heterogeneity. Suspensions appear non-uniform and can separate over time, with the solid particles settling at the bottom. Opacity. Suspensions scatter light, giving them a cloudy or opaque appearance. Examples: muddy water, orange juice with pulp, and a mixture of sand and water. 3. Colloids. Colloids are heterogeneous mixtures in which fine particles, between the sizes of solutions and suspensions, are dispersed in a continuous medium. The particles in colloids do not settle out or separate easily, and they can scatter light, causing a milky or translucent appearance. Here are some key characteristics. Particle size. Colloidal particles are larger than those in solutions but smaller than those in suspensions, typically ranging from 1 nanometer to 1 micrometer in size. Heterogeneity. Colloids appear uniform to the naked eye but may show slight inhomogeneity under a microscope. Light scattering. Colloidal particles can scatter light, resulting in a milky or translucent appearance. Examples: milk, gelatin, fog, and mayonnaise. These distinctions highlight the differences in particle size, homogeneity, light scattering properties, and stability between solutions, suspensions, and colloids. It's important to note that these categories exist on a spectrum, and some mixtures may exhibit characteristics of more than one category depending on the specific circumstances. Here are different types of solutions based on the solute-solvent combinations and their characteristics. 1. Aqueous solutions. Aqueous solutions are solutions in which water is the solvent. Water is an excellent solvent for many substances due to its polarity and ability to form hydrogen bonds. Examples include salt water, sodium chloride dissolved in water, sugar dissolved in water, and hydrochloric acid dissolved in water. 2. Solid solutions. Solid solutions are solutions in which the solvent is a solid. The solute particles are dispersed and uniformly mixed within the solid solvent. Examples include alloys like bronze, a mixture of copper and tin, and stainless steel, a mixture of iron, chromium, and nickel. 3. Gaseous solutions. Gaseous solutions, also known as gas mixtures, are solutions in which the solvent is a gas. The solute gas molecules are evenly dispersed within the gas solvent. Examples include air, a mixture of gases like nitrogen, oxygen, carbon dioxide, and others, and carbonated beverages, carbon dioxide gas dissolved in a liquid. 4. Liquid solutions. Liquid solutions are solutions in which the solvent is a liquid. The solute is dissolved within the liquid solvent. Examples include ethanol dissolved in water, commonly known as alcohol or alcoholic beverages, antifreeze, ethylene glycol dissolved in water, and vinegar, acetic acid dissolved in water. 5. Supersaturated solutions. Supersaturated solutions are solutions in which the concentration of the solute exceeds its normal solubility limit at a given temperature. These solutions are created by dissolving the solute in a solvent at a higher temperature and then slowly cooling it down. Supersaturated solutions are unstable and can be easily triggered to precipitate excess solute. An example is a supersaturated solution of sugar or salt in water. 6. Dilute and concentrated solutions. Dilute solutions have a relatively small amount of solute dissolved in the solvent. The concentration of the solute is low. Concentrated solutions, on the other hand, have a relatively large amount of solute dissolved in the solvent. The concentration of the solute is high. The terms dilute and concentrated are relative and depend on the specific solute-solvent system. These are some examples of different types of solutions based on the nature of the solute and solvent involved. Solutions can vary greatly in their properties and applications, depending on the specific components involved and the conditions under which they are prepared. When investigating the effect of temperature on the solubility of solids in water, there are general trends to observe. However, it's important to note that the solubility of different solutes can vary, and specific solubility curves or equations may be available for particular substances. Here's a general understanding of how temperature affects the solubility of solids in water. 1. Generally, for many solids, an increase in temperature leads to an increase in solubility. This means that more solute can dissolve in water as the temperature rises. 2. The relationship between temperature and solubility can vary depending on the specific solute. Some solutes show a significant increase in solubility with temperature, while others may show only a slight or negligible change. 3. In many cases, the increase in temperature provides more energy to the system, allowing the water molecules to move more vigorously and break the intermolecular forces holding the solute particles together. This enhanced molecular motion helps the solute particles mix more effectively with the solvent, leading to greater solubility. 4. However, there are exceptions where the solubility of a solute decreases with increasing temperature. This is often observed in cases where the dissolution process is exothermic, meaning it releases heat. As the temperature rises, the additional energy disrupts the equilibrium between dissolved and undissolved solute, causing the solute to come out of solution. 5. It's worth noting that some solutes have a maximum solubility at a specific temperature. This means that beyond a certain temperature, the solubility starts to decrease, forming a saturation point. 6. The effect of temperature on solubility can be described by solubility curves, which show how the solubility of a solute changes with temperature. These curves can vary for different solutes and can be experimentally determined. When investigating the effect of temperature on the solubility of solids in water, you can perform experiments by dissolving a fixed amount of a solid solute in water at different temperatures, allowing it to reach equilibrium, and measuring the amount of solute dissolved. By analyzing the data obtained, you can observe and analyze the relationship between temperature and solubility for that particular solute. Remember to consider safety precautions when conducting experiments and follow appropriate guidelines. Additionally, For specific solutes, it is recommended to consult solubility tables or publish data to understand their behavior more accurately. Here are some common separation techniques based on differences in properties of the components of mixtures. 1. Filtration. Filtration is used to separate solid particles from a liquid or gas based on differences in particle size. It involves passing the mixture through a filter medium that allows the liquid or gas to pass through while retaining the solid particles. Filtration is effective when the solid particles are larger than the pore size of the filter. 2. Distillation. Distillation is a technique used to separate a mixture of liquids based on differences in boiling points. The mixture is heated, and the component with the lower boiling point vaporizes first. The vapor is then condensed and collected, resulting in the separation of the components. Distillation is effective when the boiling points of the components differ significantly. 3. Evaporation. Evaporation is used to separate a dissolved solid from a liquid. The mixture is heated, causing the liquid to evaporate, leaving behind the solid residue. Evaporation is effective when the boiling point of the solvent is significantly lower than that of the dissolved solid. 4. Centrifugation. Centrifugation is a method used to separate solid particles or denser liquids from a mixture by rotating it rapidly. The centrifugal force causes the denser components to settle at the bottom while the lighter components remain in the supernatant. Centrifugation is effective when there is a noticeable difference in density between the components. 5. Chromatography. Chromatography is a technique used to separate the components of a mixture based on their differential affinities to a stationary phase and a mobile phase. The components travel at different rates through the stationary phase, leading to their separation. Different types of chromatography, such as paper chromatography or column chromatography, can be used depending on the specific mixture and its components. 6. Magnetic separation. Magnetic separation is employed to separate magnetic materials from a mixture using a magnetic field. The magnetic component is attracted to a magnet, allowing for its separation from the non-magnetic components. Magnetic separation is effective when one component of the mixture possesses magnetic properties. 7. Decantation. Decantation is a simple separation technique used to separate a mixture of a solid and a liquid by pouring off the liquid without disturbing the settled solid. Decantation is effective when the solid particles are larger and settle at the bottom of the container. 8. Extraction. Extraction is a technique used to separate components based on their solubilities in different solvents. By selecting a solvent in which one component is soluble while the other is insoluble, the components can be separated. The mixture is typically shaken or stirred with the solvent, and the two immiscible phases are then separated. These are just a few examples of separation techniques based on differences in properties of the components in a mixture. The choice of technique depends on the specific mixture, the properties of its components, and the desired outcome of the separation. The extraction of sucrose from sugar cane involves several steps to obtain the desired product. Here is a general description of the process. 1. Harvesting and crushing. Sugar cane is harvested by cutting the stalks close to the ground when they have reached maturity. The harvested cane is then transported to the processing plant. At the plant, the sugar cane stalks are washed to remove dirt and debris and then crushed to extract the juice. 2. Juice extraction. The crushed sugar cane undergoes a process known as milling, where the juice is extracted from the fiber. This is typically done using heavy rollers that squeeze out the juice. The extracted juice contains the dissolved sucrose, along with other impurities such as plant fibers, proteins, and minerals. 3. Clarification. To remove the impurities from the sugar cane juice, a clarification process is carried out. The juice is heated and treated with lime, calcium oxide or calcium hydroxide, to raise the pH and facilitate the precipitation of impurities. The impurities form a solid mass called scum or bagasse that can be removed through filtration or settling. 4. Evaporation. The clarified sugar cane juice is then concentrated through evaporation. The juice is heated in multiple stages in evaporators, which remove water and increase the sugar concentration. As water is evaporated, the juice thickens, and its sugar content rises. 5. Crystallization. Once the juice has been concentrated to a specific sugar concentration, it undergoes further processing to induce the crystallization of sucrose. This is typically done by cooling the concentrated juice and initiating the formation of sugar crystals. The sugar crystals grow and form a solid mass known as a sugar crystal slurry. 6. Separation and drying. The sugar crystal slurry is then separated from the remaining liquid through centrifugation. The centrifuge separates the crystals from the syrup, with the syrup being spun out while the sugar crystals remain behind. The separated sugar crystals are then dried to remove any remaining moisture, resulting in the production of raw sugar. 7. Refining. Raw sugar is often further processed to remove impurities and produce refined white sugar. The refining process involves multiple stages, including washing, filtration, decolorization, and recrystallization. These processes help remove residual impurities and produce pure, white sucrose crystals. 8. Packaging. The final step involves packaging the refined sugar into appropriate containers, such as bags or boxes, ready for distribution and consumption. It's important to note that the exact extraction process may vary depending on the specific equipment and techniques used in different sugar mills and refineries. However, the general steps described above provide an overview of the extraction of sucrose from sugarcane. 1. Atoms. Atoms are the basic building blocks of matter. They are the smallest unit of an element that retains the chemical properties of that element. Atoms are composed of three main subatomic particles. Protons, positively charged particles found in the nucleus of an atom. Protons contribute to the atomic mass and determine the element's identity. Neutrons, neutral particles found in the nucleus of an atom. Neutrons also contribute to the atomic mass. Electrons, negatively charged particles that orbit the nucleus in specific energy levels or electron shells. Electrons are much smaller and lighter than protons and neutrons. They determine the chemical behavior and reactivity of an atom. 2. Nucleus. The nucleus is the central part of an atom, containing protons and neutrons. It has a positive charge due to the presence of protons. The nucleus is extremely dense and accounts for most of the atom's mass. 3. Electron shells. Electrons are arranged in energy levels or electron shells surrounding the nucleus. These shells are designated as the first shell, closest to the nucleus, and subsequent shells, further away. Each shell has a maximum number of electrons it can hold. The first shell can hold up to 2 electrons, while the second and higher shells can hold more. 4. Atomic number. The atomic number of an atom is equal to the number of protons in the nucleus. It uniquely identifies each element on the periodic table. For a neutral atom, the atomic number also represents the number of electrons. 5. Mass number. The mass number of an atom is the sum of protons and neutrons in the nucleus. It gives the approximate mass of the atom. Isotopes are atoms of the same element with different numbers of neutrons, resulting in different mass numbers. 6. Electron configuration. The electron configuration describes how electrons are distributed among the various electron shells and orbitals within an atom. It follows a set of rules based on the energy levels and sublevels. The electron configuration determines the chemical properties and behavior of an element. 7. Energy levels and sublevels. Energy levels represent the major regions or shells where electrons can be found. These levels are labeled with the numbers 1, 2, 3, and so on. Within each energy level, there are sublevels or subshells, designated by letters S, P, D, F. Each sublevel can hold a specific number of electrons. Understanding the atomic structure helps explain the behavior and properties of elements, as well as the formation of chemical bonds and interactions between atoms. It forms the foundation of chemistry and our understanding of matter at the microscopic level. Here's a description of the atomic structure of elements with atomic number 1 to 20, along with illustrations showing the arrangement of subatomic particles within their atoms. 1. Hydrogen, H, atomic number 1. Hydrogen has 1 proton in its nucleus and 1 electron in its electron shell. Illustration. H. 1. 2. Helium, He, atomic number 2. Helium has 2 protons and 2 neutrons in its nucleus. It has 2 electrons in its electron shell. Illustration. He. 2. 3. Lithium, Li, atomic number 3. Lithium has 3 protons and 4 neutrons in its nucleus. It has 3 electrons in its electron shells, with 2 in the first shell and 1 in the second shell. Illustration. Li. 3. 4. Beryllium, B, atomic number 4. Beryllium has 4 protons and 5 neutrons in its nucleus. It has 4 electrons in its electron shells, with 2 in the first shell and 2 in the second shell. Illustration. B. 4. 5. Boron, B, atomic number 5. Boron has 5 protons and 6 neutrons in its nucleus. It has 5 electrons in its electron shells, with 2 in the first shell and 3 in the second shell. Illustration. B. 5. 6. Carbon, C, atomic number 6. Carbon has 6 protons and 6 neutrons in its nucleus. It has 6 electrons in its electron shells, with 2 in the first shell and 4 in the second shell. Illustration. C. 6. 7. Nitrogen, N, atomic number 7. Nitrogen has 7 protons and 7 neutrons in its nucleus. It has 7 electrons in its electron shells, with 2 in the first shell and 5 in the second shell. Illustration. N. 7. 8. Oxygen, O, atomic number 8. Oxygen has 8 protons and 8 neutrons in its nucleus. It has 8 electrons in its electron shells, with 2 in the first shell and 6 in the second shell. Illustration. O. 8. 9. Fluorine, F, atomic number 9. Fluorine has 9 protons and 10 neutrons in its nucleus. It has 9 electrons in its electron shells, with 2 in the first shell and 7 in the second shell. Illustration. F. 9. 10. Neon, Ne, atomic number 10. Neon has 10 protons and 10 neutrons in its nucleus. It has 10 electrons in its electron shells, with 2 in the first shell and 8 in the second shell. Illustration. Ne. 10. The illustrations above show the arrangement of protons, red, neutrons, blue, and electrons, black dots, within the atoms of elements with atomic number 1 to 10. The atomic structure of elements with atomic number 11 to 20 follows similar patterns, with an increasing number of protons, neutrons, and electrons in their respective shells. Here are the properties of electrons, protons, and neutrons. Electrons. 1. Charge. Electrons have a negative charge, -1. 2. Mass. Electrons have a very small mass, approximately 1/1836 of the mass of a proton or neutron. 3. Location. Electrons orbit around the nucleus of an atom in specific energy levels or electron shells. 4. Relative size. Electrons are much smaller in size compared to protons and neutrons. 5. Role. Electrons determine the chemical behavior and reactivity of an atom. The arrangement of electrons in the electron shells determines the atom's chemical properties and its ability to form bonds with other atoms. Protons. 1. Charge. Protons have a positive charge, +1. 2. Mass. Protons have a relatively larger mass compared to electrons. Their mass is approximately 1 atomic mass unit, AμU. 3. Location. Protons are located in the nucleus of an atom. 4. Relative size. Protons are larger in size compared to electrons. 5. Role. Protons determine the atomic number and identity of an element. The number of protons in an atom's nucleus defines the element and its unique properties. Neutrons. 1. Charge. Neutrons have no charge and are neutral, 0. 2. Mass. Neutrons have a mass similar to protons. Their mass is approximately 1 atomic mass unit, mu. 3. Location. Neutrons are located in the nucleus of an atom, alongside protons. 4. Relative size. Neutrons are slightly larger in size compared to protons. 5. Role. Neutrons contribute to the atomic mass of an atom. Different isotopes of an element have the same number of protons but differ in the number of neutrons. It's important to note that the properties mentioned above are specific to electrons, protons, and neutrons in the context of atoms. They may exhibit different behaviors and properties in other contexts, such as in particle physics or when interacting with external fields or particles. Here are the definitions of atomic number and mass number. Atomic number. The atomic number of an atom is defined as the number of protons found in the nucleus of an atom. It is denoted by the symbol Z. Each element on the periodic table has a unique atomic number, which determines its identity. For example, hydrogen has an atomic number of 1, helium has an atomic number of 2, and so on. The atomic number is used to arrange elements in increasing order on the periodic table. In a neutral atom, the number of protons, atomic number, is equal to the number of electrons orbiting the nucleus. Changes in the atomic number result in a different element. For example, adding or subtracting protons changes the element entirely. Mass number. The mass number of an atom is defined as the sum of the number of protons and neutrons in the nucleus of an atom. It is denoted by the symbol A. The mass number represents the approximate mass of an atom and is expressed in atomic mass units, mu. For example, consider an atom with atomic number Z and mass number A. This indicates that the nucleus of the atom contains Z protons and A Z neutrons. The mass number is used to distinguish between different isotopes of an element. Isotopes are atoms of the same element that have the same atomic number, same number of protons, but different mass numbers, different number of neutrons. To summarize, the atomic number represents the number of protons in an atom's nucleus, while the mass number represents the sum of protons and neutrons. Together, they provide important information about the identity and characteristics of an atom. Relative atomic mass, also known as atomic weight, is a weighted average mass of the isotopes of an element relative to the mass of an atom of carbon-12. It is denoted by the symbol R. Elements can have multiple isotopes, which are atoms of the same element with different numbers of neutrons in their nuclei. These isotopes have different mass numbers but the same atomic number, number of protons. The relative atomic mass takes into account the abundance, percentage occurrence, of each isotope and calculates an average mass based on their relative proportions. The relative atomic mass is expressed in atomic mass units, mu, or unified atomic mass units, U. It is a dimensionless quantity that compares the mass of an atom to the mass of an atom of carbon-12, which is assigned a relative atomic mass of exactly 12. Therefore, the relative atomic mass of an element tells us how much heavier or lighter an atom of that element is compared to carbon-12. For example, the relative atomic mass of oxygen, O, is approximately 16. This means that, on average, an oxygen atom is 16 times heavier than 1/12 the mass of a carbon-12 atom. It's important to note that the relative atomic mass listed on the periodic table is an average value due to the presence of different isotopes. The actual mass of an individual atom may vary slightly depending on the specific isotope present. The relative atomic mass is a useful value in chemistry and physics as it provides a standard reference for comparing the masses of different atoms and elements. The notation of the form ACXBD represents the shorthand notation used to describe the atomic structure of an atom or ion, where X represents the chemical symbol of the element. Here's how to interpret each component of the notation. A. This represents the mass number or the total number of protons and neutrons in the nucleus of the atom or ion. It indicates the sum of protons and neutrons. C. This represents the charge of the atom or ion. If the atom or ion is neutral, no charge, this value is omitted. If the atom or ion is charged, the value of C indicates the magnitude of the charge. A positive value of C indicates a cation, an atom or ion with a positive charge, while a negative value of C indicates an anion, an atom or ion with a negative charge. X, this represents the chemical symbol of the element, which is a 1 or 2-letter abbreviation used to represent a specific element. For example, H represents hydrogen, Na represents sodium, O represents oxygen, and so on. B, this represents the atomic number or the number of protons in the nucleus of the atom or ion. The atomic number uniquely identifies an element. D, this indicates the number of electrons in the atom or ion. For a neutral atom, the number of electrons is equal to the number of protons, so this value is often omitted. If the atom or ion has gained or lost electrons, D indicates the deviation from the number of protons. Here are a few examples to illustrate the interpretation of the notation. 1. 12(6)C. This notation represents the carbon atom. The mass number is 12, indicating the sum of protons and neutrons. The atomic number is 6, representing the number of protons. Since there is no charge mentioned, it indicates a neutral carbon atom. 2. 2311Na+1. This notation represents a sodium ion with a +1 charge. The mass number is 23, indicating the sum of protons and neutrons. The atomic number is 11, representing the number of protons. The +1 charge indicates that the ion has lost 1 electron compared to a neutral sodium atom. 3. 16802. This notation represents an oxygen ion with a -2 charge. The mass number is 16, indicating the sum of protons and neutrons. The atomic number is 8, representing the number of protons. The -2 charge indicates that the ion has gained 2 electrons compared to a neutral oxygen atom. In summary, the notation ACXBD provides information about the mass number, charge, chemical symbol, atomic number, and the number of electrons of an atom or ion, allowing for a concise representation of its atomic structure. Isotopy refers to the phenomenon where different isotopes of an element have the same atomic number, number of protons, but differ in their mass numbers, number of protons and neutrons. Isotopes of an element have similar chemical properties since they have the same number of electrons and protons, but they may exhibit different physical properties due to variations in their atomic mass. Isotopes are denoted by the element's chemical symbol along with the mass number as a superscript to the left of the symbol. For example, carbon-12 and carbon-14 are isotopes of carbon, where 12 and 14 represent their respective mass numbers. Isotopes arise due to differences in the number of neutrons in the atomic nucleus. For instance, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. This variation in the number of neutrons gives rise to different atomic masses for isotopes of the same element. Isotopes can have different natural abundances, which refer to the relative proportions of each isotope in a naturally occurring sample of an element. The atomic weight or relative atomic mass of an element, as listed on the periodic table, takes into account the masses and abundances of all its isotopes. Isotopes find applications in various fields, including radiometric dating, nuclear medicine, and environmental studies. By analyzing the isotopic composition of elements, scientists can gain insights into the origin, age, and behavior of materials and processes in different systems. In summary, isotopy refers to the existence of multiple isotopes of an element, where they have the same number of protons, atomic number, but different numbers of neutrons, resulting in different mass numbers. Isotopes play a crucial role in understanding atomic structure, chemical behavior, and various scientific applications. Radioactive isotopes, also known as radioisotopes, have numerous applications in various fields. Here are some common uses of radioactive isotopes. 1. Medicine. Radioisotopes are widely used in medical diagnostics and treatments. Some examples include diagnostic imaging. radioisotopes such as technetium-99m, Tc-99m, are used in imaging techniques like single-photon emission computed tomography, SPECT, and positron emission tomography, PET, to visualize and diagnose diseases. Radiation therapy, radioisotopes like iodine-131, I-131, and cobalt-60, Co-60, are used in cancer treatments, where radiation is targeted at cancer cells to destroy them. 2. Industry. Radioisotopes find applications in various industrial processes, including quality control. Radioisotopes can be used to test the integrity and quality of materials and products, such as checking for leaks in pipes or monitoring thickness in manufacturing processes. Sterilization. Radioisotopes like cobalt-60, Co-60, can be used for sterilization purposes in the medical, pharmaceutical, and food industries, effectively killing microorganisms. 3. Agriculture. Radioisotopes are used in agriculture to study plant and soil behavior, improve crop yields, and protect against pests. Examples include radiotracer techniques. Radioisotopes are used as tracers to study the uptake and movement of nutrients in plants, helping to optimize fertilization techniques. Pest control. Radioisotopes like cobalt-60, Co-60, are used in insect pest control programs to sterilize male insects, reducing their ability to reproduce. 4. Archaeology and geology. Radioisotopes are used to determine the age of artifacts, fossils, and geological formations. The most well-known example is carbon-14 dating, which is used to estimate the age of organic materials up to around 50,000 years old. 5. Energy and nuclear power. Radioisotopes play a crucial role in nuclear power generation and research, including the production of electricity and the study of nuclear reactions. 6. Environmental studies. Radioisotopes are used to trace and study environmental processes, including the movement of pollutants, tracking water flow, and monitoring air pollution. It's important to note that the use of radioactive isotopes requires strict safety protocols and regulations to ensure the protection of human health and the environment. Here's what you can do for the topic periodic table and periodicity. For point 1, explain the organization of the periodic table and the significance of periods and groups. For point 2, identify the different regions and blocks in the periodic table. For point 3, define atomic radius and explain how it changes across periods and down groups. For point 4, define ionization energy and explain how it changes across periods and down groups. For point 5, define electronegativity and explain how it changes across periods and down groups. For point 6, explain the concept of periodicity and how it relates to the periodic table. For point 7, identify and explain the periodic trends in atomic radius, ionization energy, and electronegativity. For point 8, explain the periodic trends in metallic and non-metallic character. For point 9, discuss the relationship between the position of an element in the periodic table and its chemical properties. Feel free to choose any of the above tasks, and I'll be happy to provide you with the information you need. The arrangement of elements in the periodic table is based on the periodic law, which states that the properties of elements are periodic functions of their atomic numbers. The periodic table organizes elements in a way that groups elements with similar properties together and allows for the identification of trends and patterns. The primary basis for the arrangement of elements in the periodic table is the increasing order of atomic numbers. The atomic number of an element represents the number of protons in the nucleus of its atom. As elements are ordered by atomic number, they are also arranged in such a way that elements with similar properties are grouped together in columns called groups or families. The periodic table is divided into periods, horizontal rows, and groups, vertical columns. Each period represents a new energy level or shell of electrons, with elements in the same period having the same number of electron shells. The period number corresponds to the highest energy level that contains electrons in that period. Within each group, elements have similar outer electron configurations, which contributes to their similar chemical properties. Elements in the same group often have similar valence electron configurations and exhibit similar trends in reactivity and bonding behavior. The periodic table is also divided into different blocks based on the electron subshells being filled. The blocks include the S block, P block, D block, and F block. The placement of elements in these blocks reflects the filling of electron orbitals and provides information about their electron configurations. In summary, the arrangement of elements in the periodic table is based on their increasing atomic numbers, which leads to the identification of trends and patterns in their properties. The table's structure, including periods, groups, and blocks, reflects the organization of elements with similar properties and electron configurations. This arrangement enables scientists to predict and understand the behavior and characteristics of elements based on their position in the periodic table. Group 2 of the periodic table, also known as the alkaline earth metals group, includes the elements beryllium, B, magnesium, milligram, calcium, Ca, strontium, Ca, barium, Ba, and radium, Ra. These elements share similar chemical properties and exhibit certain trends as you move down the group. Here are the trends in Group 2. 1. Atomic radius. As you move down Group 2, the atomic radius increases. This is because each successive element has an additional electron shell or energy level compared to the previous element. The increase in electron shells leads to an increase in atomic size. 2. Ionization energy. Ionization energy is the energy required to remove an electron from an atom. In Group 2, ionization energy decreases as you move down the group. This is because the outermost electron in each element is located in a higher energy level, farther away from the nucleus. As a result, it is less tightly held by the positively charged nucleus, making it easier to remove. 3. Reactivity. Group 2 elements are highly reactive metals. As you move down the group, the reactivity increases. This is due to the decrease in ionization energy. Lower ionization energy means that it is easier for Group 2 elements to lose their outermost electrons and form positive ions. They readily react with nonmetals, such as oxygen and halogens, to form compounds. 4. Electronegativity. Electronegativity is the tendency of an atom to attract electrons towards itself in a chemical bond. In Group 2, electronegativity decreases as you move down the group. The atoms of these elements have larger atomic sizes and weaker attractive forces on their outermost electrons, resulting in lower electronegativities. 5. Melting and boiling points. The melting and boiling points of Group 2 elements generally decrease as you move down the group. This is because the metallic bonding in these elements weakens with increasing atomic size. As a result, it takes less energy to overcome the metallic bonds and transition from the solid to liquid or gaseous state. These trends in Group 2 illustrate the general behavior of alkaline earth metals as you move down the group. However, it's important to note that there may be some variations or anomalies among specific elements in certain trends due to factors such as electron shielding and nuclear charge. Group 7 of the periodic table, also known as Group 17 or the halogens group, consists of the elements fluorine, F, chlorine, Cl, bromine, Br, iodine, I, and astatine, At. These elements share similar chemical properties and exhibit certain trends as you move down the group. Here are the trends in Group 7. 1. Atomic radius. As you move down Group 7, the atomic radius increases. This is because each successive element has an additional electron shell or energy level compared to the previous element. The increase in electron shells leads to an increase in atomic size. 2. Ionization energy. Ionization energy is the energy required to remove an electron from an atom. In Group 7, ionization energy generally decreases as you move down the group. This is because the outermost electron in each element is located in a higher energy level, farther away from the nucleus. As a result, it is less tightly held by the positively charged nucleus, making it easier to remove. 3. Reactivity. Group 7 elements are highly reactive nonmetals. As you move down the group, the reactivity decreases. This is because the atomic size increases, making it more difficult for the outermost electron to be involved in chemical reactions. Fluorine is the most reactive element in the group, readily forming compounds with other elements, while astatine is the least reactive. 4. Electronegativity. Electronegativity is the tendency of an atom to attract electrons towards itself in a chemical bond. In group 7, electronegativity generally decreases as you move down the group. The atoms of these elements have larger atomic sizes and weaker attractive forces on their outermost electrons, resulting in lower electronegativities. 5. Melting and boiling points. The melting and boiling points of group 7 elements generally increase as you move down the group. This is because the intermolecular forces, such as van der Waals forces, become stronger with increasing atomic size. As a result, more energy is required to break these forces and transition from the solid to liquid or gaseous state. It's important to note that there may be some variations or anomalies among specific elements in certain trends due to factors such as electron shielding and nuclear charge. Additionally, astatine, AT, is a rare and radioactive element with limited information available, so its properties and trends may not be as well documented as the other elements in group 7. In period 3 of the periodic table, several trends can be observed as you move from left to right across the period. Here are some key trends in period 3. 1. Atomic radius. The atomic radius generally decreases across period 3 from left to right. This is because, as you move across the period, the number of protons in the nucleus increases, resulting in a greater positive charge. This increased nuclear charge attracts the electrons more strongly, leading to a contraction of the atomic size. 2. Ionization energy. Ionization energy, which is the energy required to remove an electron from an atom, generally increases across period 3 from left to right. As you move across the period, the atomic size decreases, and the outermost electrons are held more tightly by the increasing nuclear charge. Therefore, more energy is required to remove an electron. 3. Electronegativity. Electronegativity is the tendency of an atom to attract electrons in a chemical bond. Electronegativity generally increases across period 3 from left to right. As the atomic size decreases and the nuclear charge increases, the atom has a greater ability to attract electrons towards itself in a bond. 4. Metallic and non-metallic character. The metallic character generally decreases across period 3 from left to right, while the non-metallic character increases. Elements on the left side of the period, such as sodium and magnesium, are metallic and tend to lose electrons to form positive ions. Elements on the right side of the period, such as chlorine and argon, are non-metallic and tend to gain electrons to form negative ions. 5. Oxidation states. The oxidation states of elements in period 3 vary. Metals such as sodium, Na, and magnesium, milligram, tend to exhibit a +1 and +2 oxidation state, respectively, by losing electrons. Non-metals such as chlorine, Cl, and sulfur, S, tend to exhibit negative oxidation states by gaining electrons. 6. Melting and boiling points. The melting and boiling points of elements in period 3 generally increase from left to right. Metallic elements, such as sodium and magnesium, have relatively low melting and boiling points. Non-metallic elements, such as chlorine and sulfur, have higher melting and boiling points. Silicon Si, a metalloid in period 3, has a high melting point. These trends in period 3 reflect the changes in atomic size, electron configuration, and bonding characteristics as you move across the period. However, it's important to note that there can be exceptions and variations among specific elements within the period due to factors such as electron shielding and the arrangement of electron orbitals. Predicting the properties of unknown elements based on their position in the periodic table involves considering the trends and patterns observed among elements with similar characteristics. While there can be variations and exceptions, the general trends provide a basis for making predictions. Here are some key considerations. 1. Atomic number and group. Elements in the same group tend to have similar properties. Therefore, if the unknown element is located in a particular group, its properties can be predicted to be similar to other elements in that group. For example, if the unknown element is located in group I, it is likely to be a highly reactive metal. 2. Period. The period of the unknown element indicates the number of electron shells or energy levels. Elements in the same period tend to have similar trends in terms of atomic size, ionization energy, and electronegativity. For example, if the unknown element is located in period 3, it would have 3 electron shells and exhibit trends similar to other elements in that period. 3. Metal, non-metal, or metalloid. The position of the unknown element in the periodic table can provide insights into its classification as a metal, non-metal, or metalloid. Elements on the left side of the periodic table, groups 1 to 12, tend to be metals, while elements on the right side, groups 13 to 18, tend to be non-metals. Elements along the staircase line, such as silicon, are classified as metalloids. Therefore, if the unknown element is located to the left of the staircase line, it is likely to be a metal. 4. Trends in physical and chemical properties. By observing the trends in atomic radius, ionization energy, electronegativity, and other properties as you move across a period or down a group, you can make predictions about the unknown element's properties. For example, if the unknown element is located in a group with increasing ionization energy and electronegativity, it is likely to have similar trends. It's important to note that while predictions can be made based on the periodic trends, there can be exceptions and variations due to factors such as electron configuration, nuclear charge, and other external influences. Experimental data and further analysis are necessary to confirm the properties of unknown elements. Here are some key points related to structure and bonding that you may find helpful. 1. Atomic structure. Atoms consist of a nucleus, which contains protons and neutrons, surrounded by electrons in energy levels or electron shells. The electrons occupy specific orbitals within the shells. 2. Valence electrons. Valence electrons are the electrons in the outermost energy level of an atom. They determine the chemical properties of an element and are involved in bonding. 3. Chemical bonds. Chemical bonds are formed when atoms interact and share, gain, or lose electrons to achieve a stable electron configuration. The main types of chemical bonds are ionic bonds, covalent bonds, and metallic bonds. 4. Ionic bonds. Ionic bonds occur when electrons are transferred from one atom to another, resulting in the formation of positively charged cations and negatively charged anions. The oppositely charged ions are held together by electrostatic forces. 5. Covalent bonds. Covalent bonds occur when atoms share electrons. They can be polar or non-polar depending on the electronegativity difference between the atoms involved. In a polar covalent bond, there is an uneven sharing of electrons, creating partial charges. 6. Metallic bonds. Metallic bonds are found in metals and involve a sea of delocalized electrons that are shared among a lattice of positive metal ions. This allows metals to conduct heat and electricity and have malleability and ductility. 7. Lewis structures. Lewis structures are diagrams that show the arrangement of electrons in a molecule or ion. They consist of chemical symbols representing the atoms and dots or lines representing the valence electrons. 8. Intermolecular forces. Intermolecular forces are forces of attraction between molecules. They include London dispersion forces, dipole-dipole interactions, and hydrogen bonding. These forces influence the physical properties of substances, such as boiling point and solubility. 9. VSEPR theory. The VSEPR, valence shell electron pair repulsion, theory predicts the shapes of molecules based on the repulsion between electron pairs around the central atom. It helps determine the molecular geometry and bond angles. 10. Hybridization. Hybridization is the mixing of atomic orbitals to form hybrid orbitals that participate in bonding. It explains the observed molecular geometries in molecules and ions. These points provide a brief overview of key concepts related to structure and bonding. If you have any specific questions or require more in-depth information on a particular subtopic, please let me know. I'll explain the formation of ionic and covalent bonds. 1. Ionic bonds. Ionic bonds are formed between atoms when there is a large difference in electronegativity, the ability of an atom to attract electrons, between them. Typically, this occurs between metals and nonmetals. Here's how ionic bonds form. In an ionic bond, one atom, the metal, donates one or more electrons to another atom, the nonmetal, to achieve a stable electron configuration. The donating atom becomes a positively charged ion called a cation because it loses electrons. The receiving atom becomes a negatively charged ion called an anion because it gains electrons. The attraction between the oppositely charged ions creates an electrostatic force, which holds the ions together and forms an ionic bond. The resulting compound is called an ionic compound or salt. For example, consider the formation of sodium chloride, NaCl. Sodium, Na, has one valence electron and wants to lose it to achieve a stable electron configuration like a noble gas. Chlorine, Cl, has 7 valence electrons and wants to gain 1 electron to achieve a stable electron configuration. Sodium donates its electron to chlorine, forming Na+, cation, and Cl, anion. The electrostatic attraction between Na+ and Cl forms the ionic bond in sodium chloride, NaCl. 2. Covalent bonds. Covalent bonds are formed when atoms share electrons to achieve a stable electron configuration. This usually occurs between nonmetal atoms. Here's how covalent bonds form. In a covalent bond, atoms share one or more pairs of electrons to fulfill their electron needs and achieve a stable electron configuration. The shared electrons occupy the overlapping region of the atomic orbitals of the participating atoms. The sharing of electrons creates a bond, known as a covalent bond, which holds the atoms together. The resulting structure is called a molecule. There are 2 types of covalent bonds, nonpolar covalent bonds and polar covalent bonds. Nonpolar covalent bonds, formed between atoms with similar electronegativity, resulting in equal sharing of electrons. Examples include diatomic molecules like hydrogen, H2, and oxygen, O2. Polar covalent bonds, formed between atoms with different electronegativity, resulting in an uneven sharing of electrons. The atom with higher electronegativity attracts the shared electrons more strongly, developing a partial negative charge, while the other atom has a partial positive charge. Examples include H2O, water, and HCl, hydrochloric acid. It's important to note that the distinction between ionic and covalent bonds is not always clear-cut, and there can be varying degrees of ionic and covalent character in different compounds. The concept of electronegativity difference helps determine the type of bond formed, but in reality, bonds exist on a continuum between purely ionic and purely covalent. The likelihood of an atom forming an ionic or a covalent bond can be predicted based on several factors related to atomic structure. Here are some considerations. 1. Electronegativity difference. Electronegativity is a measure of an atom's ability to attract electrons towards itself in a chemical bond. If the electronegativity difference between 2 atoms is large, typically greater than 1.7, it indicates a significant difference in electronegativity and suggests the formation of an ionic bond. In contrast, if the electronegativity difference is small, typically less than 1.7, it indicates a moderate or low difference and suggests the formation of a covalent bond. 2. Metal and nonmetal. In general, atoms of metals tend to form ionic bonds with atoms of nonmetals. Metals have low electronegativity and readily lose electrons to achieve a stable electron configuration, forming positive ions, cations. Nonmetals, on the other hand, have higher electronegativity and readily gain electrons to achieve a stable electron configuration, forming negative ions, anions. The electrostatic attraction between the positive and negative ions leads to the formation of an ionic bond. 3. Valence electrons. The number of valence electrons an atom possesses can also indicate the likelihood of forming an ionic or covalent bond. Atoms with few valence electrons, 1, 2, or 3, are more likely to lose those electrons and form positive ions, favoring ionic bonding. Conversely, atoms with more valence electrons, 5, 6, or 7, are more likely to gain electrons and form negative ions, also favoring ionic bonding. Atoms with 4 valence electrons tend to share electrons and form covalent bonds. 4. Stability. atoms tend to form bonds in order to achieve a more stable electron configuration, usually resembling a noble gas configuration. Noble gases have a full complement of valence electrons and are considered highly stable. Therefore, atoms that can gain or lose electrons to achieve a noble gas configuration are more likely to form ionic bonds. Atoms that can share electrons to complete their valence shell and achieve a stable configuration are more likely to form covalent bonds. It's important to note that the likelihood of an atom forming an ionic or covalent bond is not absolute and can vary depending on the specific elements involved and their respective atomic structures. Additionally, some compounds may exhibit a mix of both ionic and covalent characteristics, resulting in partially ionic or partially covalent bonds. Here's how you can write formulas to represent ions, molecules, and formula units. 1. Ions. Ions are charged particles formed when atoms gain or lose electrons. The charge of the ion is indicated as a superscript after the chemical symbol. Here are some examples. Sodium ion, Na+. Chloride ion, Cl. Calcium ion, Ca2+. Nitrate ion, NO3. Hydroxide ion, OH. 2. Molecules. Molecules are formed when atoms share electrons through covalent bonds. The chemical formula of a molecule represents the types and numbers of atoms present. Here are some examples. Water molecule, H2O. Carbon dioxide molecule, CO2. Methane molecule, CH4. Oxygen molecule, O2. Ethanol molecule, C2H6O. 3. Formula units. Formula units are used to represent ionic compounds, which are composed of positively and negatively charged ions. The chemical formula of an ionic compound represents the ratio of ions in the compound, usually in the lowest whole number ratio. Here are some examples. Sodium chloride, NaCl. Calcium carbonate, CaCO3. Magnesium oxide, mg/mol. Ammonium sulfate, NH4, 2SO4. Potassium hydroxide, KOH. In ionic compounds, the charges of the ions are balanced to ensure overall electrical neutrality. For example, in sodium chloride, NaCl, the sodium ion has a +1 charge, Na+, and the chloride ion has a -1 charge, Cl, resulting in a balanced formula. Note, parentheses are used when there is more than one of a polyatomic ion in a formula or when a subscript applies to a group of atoms. Also, when writing formulas, it is important to consider the valences or charges of the ions to ensure the proper combination. These examples illustrate how formulas are written to represent ions, molecules, and formula units. The specific elements and compounds you are working with may have different formulas, so it's important to determine the correct ratios and charges of the ions or atoms involved. Metallic bonding is a type of chemical bonding that occurs between metal atoms within a metallic solid. It is responsible for the unique properties exhibited by metals, such as high electrical and thermal conductivity, malleability, ductility, and luster. Here's an explanation of metallic bonding. 1. Electron C model. In metallic bonding, the valence electrons of metal atoms are not strongly associated with any specific atom but are instead delocalized and free to move throughout the entire metal structure. This is known as the electron C model. 2. Delocalized electrons. Metal atoms have relatively few valence electrons, and they tend to lose these electrons to achieve a stable electron configuration. When metal atoms lose their valence electrons, they become positively charged metal ions or cations. The delocalized electrons are then attracted to the positively charged metal cations, creating a sea of mobile electrons surrounding the metal ions. 3. Formation of metallic bonds. The delocalized electrons move freely within the structure of the metal lattice and are not associated with any specific metal ion. They are shared by all the metal atoms in the crystal, creating a strong bond that holds the metal structure together. The positive metal ions are held in place by the attraction between the metal cations and the negatively charged electron C. 4. Properties of metallic bonding. The delocalized nature of the electrons in metallic bonding gives rise to several characteristic properties of metals. Electrical conductivity. The mobile electrons can carry an electric current, making metals excellent conductors of electricity. Thermal conductivity. The free electrons also transfer thermal energy rapidly, contributing to the high thermal conductivity of metals. Malleability and ductility. The mobility of the electrons allows metal atoms to slide past one another without breaking the metallic bonds. This gives metals their ability to be hammered into thin sheets, malleability, and drawn into wires, ductility. Luster. The delocalized electrons can absorb and re-emit light, giving metals their characteristic shine or luster. Overall, metallic bonding is a result of the sharing and mobility of delocalized electrons among metal atoms. This unique bonding mechanism contributes to the distinct properties and behaviors of metals, making them an essential part of various industrial, technological, and everyday applications. Let's describe ionic crystals, simple molecular crystals, and giant molecular crystals. 1. Ionic crystals. Ionic crystals are a type of solid structure formed by the arrangement of positively and negatively charged ions held together by ionic bonds. Here are some key characteristics of ionic crystals. Composition. Ionic crystals are made up of alternating positive and negative ions. The ions are typically derived from elements on opposite sides of the periodic table, such as metals and nonmetals. Structure. The ions in an ionic crystal are arranged in a three-dimensional repeating pattern called a crystal lattice. The arrangement is such that each positive ion is surrounded by negatively charged ions, and vice versa. Bonding. The bonding between ions in an ionic crystal is purely electrostatic, resulting from the attraction between oppositely charged ions. High melting points. Ionic crystals have high melting points because breaking the strong electrostatic attractions between ions requires a significant amount of energy. Brittle. Ionic crystals are generally brittle because the arrangement of ions is disrupted when a force is applied, leading to a shift in the crystal structure and subsequent fracture. Common examples of ionic crystals include sodium chloride, NaCl, calcium carbonate, CaCO3, and potassium iodide, Ki. 2. Simple molecular crystals. Simple molecular crystals are solids composed of individual molecules held together by weak intermolecular forces. Here are some features of simple molecular crystals. Composition. Simple molecular crystals consist of discrete molecules, which can be composed of the same or different types of atoms. Structure. The molecules in simple molecular crystals are arranged in a regular pattern, forming a crystal lattice. However, the interactions between molecules are relatively weak compared to the covalent bonds within the molecules. Intermolecular forces. The bonding within simple molecular crystals is primarily governed by intermolecular forces, such as van der Waals forces, dipole-dipole interactions, and hydrogen bonding. Low melting points. Simple molecular crystals have lower melting points compared to ionic crystals because the intermolecular forces between the molecules are weaker and require less energy to overcome. Often volatile. Due to the weak intermolecular forces, many simple molecular crystals are volatile and can easily transition from solid to gas phase. Examples. Common examples of simple molecular crystals include solid oxygen, O2, solid carbon dioxide, CO2, and iodine, I2. 3. Giant molecular crystals. Giant molecular crystals are solids composed of large, repeating three-dimensional networks of covalently bonded atoms or molecules. Here are some characteristics of giant molecular crystals. Composition. Giant molecular crystals consist of large molecules or atoms held together by strong covalent bonds. Structure. The atoms or molecules in giant molecular crystals are arranged in a highly ordered, repeating lattice structure. Covalent bonds. The bonding within giant molecular crystals is primarily covalent, with atoms sharing electrons to form strong bonds. High melting points. Giant molecular crystals have high melting points due to the strong covalent bonds that require substantial energy to break. Examples of giant molecular crystals include diamond, composed of carbon atoms in a tetrahedral lattice, quartz, composed of silicon and oxygen atoms, and graphite, composed of lead-carbon atoms. In summary, ionic crystals are composed of positively and negatively charged ions held together by ionic bonds. Simple molecular crystals consist of individual molecules held together by weak intermolecular forces, and giant molecular crystals are formed by large covalently bonded molecules or atoms. Each type of crystal structure exhibits distinct properties and behaviors based on the nature of their bonding and arrangement of particles. Let's distinguish between ionic and molecular solids. Ionic solids. 1. Composition. Ionic solids are composed of positively and negatively charged ions. 2. Bonding. The bonding in ionic solids is characterized by strong electrostatic attractions between oppositely charged ions. These bonds are called ionic bonds. 3. Structure. Ionic solids have a three-dimensional crystal lattice structure, where the positive and negative ions are arranged in a repeating pattern. 4. Conductivity. In the solid state, ionic solids do not conduct electricity because the ions are held in fixed positions and cannot move. However, in the molten state or when dissolved in water, they can conduct electricity due to the movement of ions. 5. Melting and boiling points. Ionic solids generally have high melting and boiling points because breaking the strong ionic bonds requires a significant amount of energy. 6. Solubility. Ionic solids are often soluble in polar solvents like water, as the polar solvent molecules can surround and separate the ions through ion-dipole interactions. Molecular solids. 1. Composition. Molecular solids are composed of individual molecules. 2. Bonding. The bonding in molecular solids is primarily due to intermolecular forces, such as van der Waals forces, dipole-dipole interactions, and hydrogen bonding. 3. Structure. Molecular solids have a crystal lattice structure where the molecules are held together by these intermolecular forces. 4. Conductivity. Molecular solids do not conduct electricity because they lack mobile charged particles, ions or free electrons, that can carry electrical current. 5. Melting and boiling points. Molecular solids generally have lower melting and boiling points compared to ionic solids because the intermolecular forces between the molecules are weaker. 6. Solubility. Molecular solids tend to be soluble in solvents with similar polarity. Polar molecules dissolve in polar solvents, while non-polar molecules dissolve in non-polar solvents, based on the principle of like dissolves like. In summary, the key differences between ionic solids and molecular solids lie in their composition, bonding, structure, conductivity, melting and boiling points, and solubility. Ionic solids are composed of ions held together by strong ionic bonds, while molecular solids are composed of individual molecules held together by intermolecular forces. Ionic solids have higher melting points, conduct electricity when molten or dissolved, and are often soluble in polar solvents, whereas molecular solids have lower melting points, do not conduct electricity, and exhibit solubility based on the polarity of the solvent and molecules. Let's relate the structure of sodium chloride, diamond, and graphite to their properties and uses. 1. Sodium chloride, NaCl. Structure. Sodium chloride has an ionic crystal structure, consisting of a repeating lattice of alternating sodium, Na+, and chloride, Cl, ions held together by strong ionic bonds. Properties. Due to its structure, sodium chloride is a hard and brittle solid with a high melting point. It is soluble in water and forms an electrolyte solution, conducting electricity when molten or dissolved. Sodium chloride also has a characteristic cubic crystal shape. Uses. Sodium chloride is commonly known as table salt and is widely used as a seasoning and preservative in food. It is also used in various industrial processes, such as chemical manufacturing, water treatment, and de-icing of roads. 2. Diamond. Structure. Diamond has a giant molecular crystal structure, where each carbon atom is covalently bonded to 4 neighboring carbon atoms in a tetrahedral arrangement. This gives diamond a three-dimensional network of strong covalent bonds. Properties. Diamond is the hardest naturally occurring substance, with exceptional hardness and high thermal conductivity. It has a high melting point and is chemically inert. Diamond is transparent and exhibits a high refractive index, making it highly lustrous. Uses: due to its extreme hardness and thermal conductivity, diamond is used in various industries. It is primarily known for its use in jewelry as gemstones, but it also has industrial applications such as cutting, grinding, drilling, and polishing tools. Diamond is also used in electronics, optics, and as a symbol of luxury. 3. Graphite. Structure: graphite has a layered or sheet-like structure, where carbon atoms are arranged in hexagonal rings and bonded covalently within each layer. The layers are held together by weak van der Waals forces. Properties: graphite is a soft and slippery solid with a low density. It is a good conductor of electricity and heat within the layers due to the presence of delocalized electrons. Graphite is opaque and has a metallic luster. Uses: graphite is commonly used as a lubricant due to its slippery nature. It is also used as a conductor in electrodes, batteries, and electrical components. Graphite finds applications in pencils, where the layers can easily slide off onto paper, leaving a mark. Additionally, it is used as a thermal insulator and in the production of graphene, a single layer of graphite with exceptional properties. In summary, the different structures of sodium chloride, diamond, and graphite contribute to their distinct properties and uses. Sodium chloride's ionic structure provides it with high melting point, solubility, and conductivity, making it suitable for culinary and industrial applications. Diamond's strong covalent bonding gives it exceptional hardness, thermal conductivity, and optical properties, making it valuable in jewelry and various industrial applications. Graphite's layered structure gives it lubricating properties, conductivity, and thermal insulation capabilities, finding uses in lubrication, electronics, and other industries. Allotropy refers to the phenomenon where an element exists in multiple forms or allotropes, each with different physical and chemical properties, despite being composed of the same type of atoms. In other words, allotropy describes the ability of an element to exist in different structural arrangements or crystal lattices. The different allotropes of an element may have variations in bonding, molecular arrangements, or crystal structures, resulting in distinct properties such as color, density, hardness, electrical conductivity, and reactivity. The transformation between different allotropes usually occurs in response to changes in temperature, pressure, or other environmental factors. Here are a few examples of elements that exhibit allotropy. 1. Carbon. Carbon is well known for its allotropes, including diamond, graphite, and fullerene. Diamond is the hardest naturally occurring substance, with a three-dimensional lattice structure consisting of covalently bonded carbon atoms. Graphite, on the other hand, has a layered structure where carbon atoms are arranged in sheets held together by weak van der Waals forces. Fullerene refers to a group of carbon allotropes composed of molecules with hollow cages or tubes, such as C60, Buckminster fullerene. 2. Oxygen. Oxygen has two common allotropes, molecular oxygen, O2, and ozone, O3. Molecular oxygen consists of two oxygen atoms bonded together, while ozone is composed of three oxygen atoms arranged in a V shape. These allotropes have different chemical reactivity and uses. Molecular oxygen is essential for respiration, while ozone plays a role in the ozone layer and has applications in water purification and sterilization. 3. Phosphorus. Phosphorus exhibits several allotropes, including white phosphorus, red phosphorus, and black phosphorus. White phosphorus is a highly reactive and toxic substance composed of tetrahedral P4 molecules. Red phosphorus is a more stable form, consisting of amorphous network structures. Black phosphorus has a layered structure similar to graphite but with stronger intralayer bonding. Allotropy is a fascinating aspect of chemistry and materials science, highlighting the ability of elements to exist in different forms with diverse properties. The study of allotropes helps deepen our understanding of the relationships between structure, bonding, and the physical and chemical behavior of elements. I apologize, but you haven't specified the task you would like me to do. Could you please provide more information or let me know what you would like me to do in relation to the topic of allotropy? Let's dive into the mole concept. 6.1 Define the mole and Avogadro's number. The mole is a unit of measurement used in chemistry to express the amount of a substance. It is defined as the amount of a substance that contains as many entities, atoms, molecules, ions, or other particles, as there are atoms in exactly 12 grams of carbon-12. The mole is represented by the symbol mol. Avogadro's number, denoted as N, is the number of entities in 1 mole of a substance. It is approximately 6.022 x 10 squared cubed entities mol. Avogadro's number is named after the Italian scientist Amedeo Avogadro, who proposed that equal volumes of gases at the same temperature and pressure contain the same number of molecules. 6.2 Define molar mass and calculate the molar mass of a compound. Molar mass is the mass of 1 mole of a substance. It is expressed in grams mole or g-mol. The molar mass of an element is numerically equal to its atomic mass, found on the periodic table, and has the unit of grams mole. To calculate the molar mass of a compound, you add up the atomic masses of all the atoms present in the compound. The atomic masses can be found on the periodic table, and they are expressed in atomic mass units, AμU. By summing up the atomic masses, you obtain the molar mass of the compound in grams mole. 6.3 Perform calculations involving moles, mass, and molar mass. The mole concept allows us to perform various calculations involving moles, mass, and molar mass. Here are some common calculations. Moles to mass. To calculate the mass of a substance from the given number of moles, you multiply the number of moles by the molar mass of the substance. Mass, G, equals number of moles x molar mass, G mol. Mass to moles. To calculate the number of moles of a substance from the given mass, you divide the mass by the molar mass of the substance. Number of moles equals mass, G, molar mass, G mol. Moles to particles. To convert the number of moles to the number of particles, atoms, molecules, ions, you multiply the number of moles by Avogadro's number. Number of particles equals number of moles x Avogadro's number. Particles to moles. To convert the number of particles to the number of moles, you divide the number of particles by Avogadro's number. Number of moles equals number of particles Avogadro's number. Mass to particles. To convert the mass of a substance to the number of particles, you first convert the mass to moles using the molar mass, and then convert the moles to particles using Avogadro's number. These calculations are essential for stoichiometry, determining empirical and molecular formulas, and solving various problems related to chemical reactions and quantities of substances. Understanding the mole concept and being able to perform these calculations is fundamental in chemistry, as it allows for precise measurements and comparisons of quantities at the atomic and molecular levels. Here are the definitions of mole and molar mass. 1. Mole. The mole is a unit of measurement used in chemistry to express the amount of a substance. It is defined as the amount of a substance that contains as many entities, atoms, molecules, ions, or other particles, as there are atoms in exactly 12 grams of carbon-12. The mole is represented by the symbol mol. The concept of the mole allows chemists to quantify and work with individual particles on a macroscopic scale. It provides a bridge between the atomic and macroscopic worlds, enabling precise measurements and calculations involving the amount of substances in chemical reactions. 2. Molar mass. Molar mass refers to the mass of 1 mole of a substance. It is expressed in grams mole or g-mol. The molar mass of an element or compound is numerically equal to its atomic or molecular mass, respectively, and has the unit of grams mole. For elements, the molar mass is equal to the atomic mass of the element, which can be found on the periodic table. For example, the molar mass of carbon, C, is approximately 12.01 grams per mole. For compounds, the molar mass is calculated by adding up the atomic masses of all the atoms in the compound. The atomic masses of the elements can also be found on the periodic table. For example, the molar mass of water, HO, is calculated by adding the atomic masses of 2 hydrogen atoms, each with a molar mass of approximately 1.01 grams per mole, and 1 oxygen atom, with a molar mass of approximately 16.00 grams per mole, resulting in a molar mass of water of approximately 18.02 grams per mole. Molar mass is used in various calculations involving moles, such as converting between mass and moles of a substance, determining the empirical and molecular formulas of compounds, and performing stoichiometric calculations in chemical reactions. In summary, the mole is a unit of measurement representing the amount of a substance, while molar mass refers to the mass of 1 mole of a substance. Both concepts are fundamental in chemistry for quantifying and calculating amounts of substances. I'll walk you through some common calculations involving the mole. 1. Converting between moles and mass. To convert between the number of moles and the mass of a substance, you can use the formula mass, G, equals number of moles x molar mass, G mole. For example, if you have 2 moles of carbon dioxide, CO2, and you want to find the mass. Mass, G, equals 2 moles x molar mass of CO2. You can find the molar mass of CO2 by adding the atomic masses of carbon, C, and 2 oxygen, O, atoms. Molar mass of CO2 equals atomic mass of C plus, 2x atomic mass of O. 2. Converting between moles and number of particles. To convert between the number of moles and the number of particles, atoms, molecules, ions, you can use Avogadro's number, 6.022 times 10 to the power of 23 particles mole. The formula is number of particles equals number of moles x Avogadro's number. For example, if you have 3 moles of water, H2O, and you want to find the number of water molecules. Number of water molecules equals 3 moles x Avogadro's number. 3. Converting between moles and volume of a gas. When dealing with gases, you can use the ideal gas law to convert between moles and volume at a given temperature and pressure. The ideal gas law is PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the ideal gas constant, and T is the temperature in Kelvin. You can rearrange this equation to solve for the number of moles. N equals PV/RT. For example, if you have a gas with a volume of 2.5 liters at a pressure of 1.2 atmospheres and a temperature of 298 Kelvin, and you want to find the number of moles. N equals 1.2 atm x 2.5 L / 0.0821 L times atm, mole times K, x 298 K. These are just a few examples of calculations involving the mole. The mole concept allows you to relate the number of particles, the mass, the volume, and other properties of a substance in a quantitative manner. It is a fundamental concept in chemistry for performing calculations and understanding the relationships between different quantities in chemical reactions and processes. Avogadro's law states that equal volumes of gases, at the same temperature and pressure, contain an equal number of particles, atoms, molecules, ions. In other words, under the same conditions, the ratio of the volumes of gases is equal to the ratio of their respective moles. The law is based on the concept that gases are composed of individual particles that are widely spaced and have negligible volume compared to the total volume occupied by the gas. Avogadro's law is a consequence of the ideal gas behavior, assuming that the gas particles do not interact with each other and follow the ideal gas equation. Mathematically, Avogadro's law can be expressed as follows. Vn equals Vn, where V and V are the volumes of the gases. N and N are the number of moles of the gases. This equation states that the ratio of the volumes is directly proportional to the ratio of the number of moles of gases. Avogadro's law is particularly useful in stoichiometry and gas calculations. It allows us to compare the relative volumes of gases involved in chemical reactions, determine the stoichiometric coefficients in a balanced chemical equation, and make predictions about the behavior of gases based on the number of moles present. It's important to note that Avogadro's law holds true for ideal gases at low pressures and high temperatures, where intermolecular interactions and volume exclusion effects are minimal. The law of conservation of matter, also known as the law of conservation of mass, states that in a closed system, matter cannot be created or destroyed. This means that the total mass of the substances present before and after a chemical reaction remains constant. According to this law, during a chemical reaction, atoms are rearranged to form new compounds or molecules, but the total number of atoms of each element involved in the reaction remains the same. In other words, the total mass of the reactants must equal the total mass of the products. The law of conservation of matter is based on the fundamental principle of the conservation of mass, which was formulated by Antoine Lavoisier in the late 18th century. Lavoisier conducted numerous experiments and observed that the total mass of the substances involved in a chemical reaction remained constant, regardless of the physical or chemical changes that occurred. This law is a cornerstone of chemistry and is essential in balancing chemical equations, calculating reaction stoichiometry, and understanding the behavior of matter in chemical reactions. It emphasizes the idea that matter is neither created nor destroyed but simply undergoes transformations and rearrangements at the atomic level. The mole concept is widely used to balance and interpret chemical equations, both for ionic and molecular substances. Here's how you can apply the mole concept to equations. 1. Balancing ionic equations. Ionic equations involve the transfer of ions between reactants to form products. To balance an ionic equation, follow these steps. A. Identify the ions present in the reactants and products. B. Determine the balanced equation by ensuring that the number of atoms of each element and the overall charge are equal on both sides of the equation. C. Use coefficients to balance the equation. These coefficients represent the mole ratios between the reactants and products. For example, let's balance the equation for the reaction between sodium hydroxide, NaOH, and hydrochloric acid, HCl, to form sodium chloride, NaCl, and water, H2O. NaOH plus HCl, NaCl plus H2O. To balance this equation, you would assign coefficients to each compound. 2 NaOH plus 2 HCl, 2 NaCl plus 2 H2O. Now, the equation is balanced, and the coefficients represent the mole ratios between the reactants and products. 2. Balancing molecular equations. Molecular equations involve the combination or rearrangement of molecules to form new substances. To balance a molecular equation, follow these steps. A. Identify the reactants and products and their respective chemical formulas. B. Determine the balanced equation by ensuring that the number of atoms of each element is equal on both sides of the equation. C. Use coefficients to balance the equation, representing the mole ratios between the reactants and products. For example, let's balance the equation for the reaction between methane, CH4, and oxygen, O2, to form carbon dioxide, CO2, and water, H2O. CH4 plus O2 CO2 plus H2O. To balance this equation, you would assign coefficients to each compound. CH4 plus 2O2 CO2 plus 2H2O. Now, the equation is balanced, and the coefficients represent the mole ratios between the reactants and products. When applying the mole concept to equations, it's important to note that the coefficients in the balanced equation represent the relative numbers of moles of each substance involved in the reaction. These coefficients allow you to calculate the stoichiometry of the reaction, determine the amount of reactants consumed or products formed, and perform mole-to-mole conversions in stoichiometric calculations. I hope this helps you understand how to apply the mole concept to both ionic and molecular equations. A standard solution, also known as a standard solution, is a solution of known concentration that is used as a reference in chemical analysis and laboratory experiments. It is prepared by accurately measuring the amount of a substance, typically a solute, and dissolving it in a known volume of solvent. The concentration of the standard solution is precisely determined through various methods, such as weighing the solute, using volumetric glassware, or performing titrations. Once the concentration is determined, the standard solution can be used to determine the concentration of other solutions or to calibrate instruments. The concept of a standard solution is based on the principle of stoichiometry and allows for accurate and reliable quantitative analysis. By using a known concentration of a substance, it provides a reference point for comparison and measurement. Standard solutions are commonly used in titrations, where the concentration of an unknown solution is determined by reacting it with a standard solution of a known concentration until an equivalence point is reached. Standard solutions are essential in various analytical techniques, such as spectrophotometry, chromatography, and pH measurements. They serve as calibration standards to validate the accuracy and reliability of measurements, ensuring consistent and reproducible results in chemical analysis. Overall, a standard solution is a solution of known concentration that serves as a reference in chemical analysis, allowing for accurate determination of the concentration of other solutions and calibration of instruments. Let's delve into the topic of acids, bases, and salts. 7.1 Define acids and bases and identify their characteristic properties. Acids are substances that, when dissolved in water, release hydrogen ions, H+. They have a sour taste, turn blue litmus paper red, and have a pH value less than 7. Acids react with bases to form salts and water in a process called neutralization. Bases, on the other hand, are substances that, when dissolved in water, release hydroxide ions, OH. They have a bitter taste, feel slippery or soapy to the touch, turn red litmus paper blue, and have a pH value greater than 7. Bases can also accept protons, H+, from acids in a neutralization reaction. 7.2 Explain the concept of pH and its significance in acid-base chemistry. pH is a measure of the acidity or alkalinity, basicity, of a solution. It represents the concentration of hydrogen ions, H+, in a solution. The pH scale ranges from 0 to 14, with 7 being neutral. Solutions with a pH less than 7 are acidic, while solutions with a pH greater than 7 are basic, alkaline. pH is logarithmic, meaning that each unit represents a tenfold difference in acidity or basicity. For example, a solution with a pH of 3 is 10 times more acidic than a solution with a pH of 4. pH is significant in acid-base chemistry because it helps quantify the strength of acids and bases, predict the behavior of substances in different pH environments, and understand the extent of proton transfer in reactions. It is a fundamental concept in many scientific fields, including chemistry, biology, environmental science, and medicine. 7.3 Classify substances as acidic, basic, or neutral based on their pH values. Substances can be classified as acidic, basic, or neutral based on their pH values. Here's a general guideline. pH less than 7, substances with a pH less than 7 are acidic. The lower the pH, the stronger the acid. Examples include hydrochloric acid, pH around 1, and lemon juice, pH around 2. pH greater than 7, substances with a pH greater than 7 are basic. The higher the pH, the stronger the base. Examples include sodium hydroxide, pH around 13, and ammonia solution, pH around 11. pH equal to 7, substances with a pH of 7 are considered neutral. Pure water has a pH of 7, indicating neutrality. It's important to note that the pH values mentioned above are approximate and can vary depending on the specific concentration and temperature of the solutions. 7.4 Describe the concept of neutralization and provide examples. Neutralization is a chemical reaction between an acid and a base that results in the formation of a salt and water. The reaction involves the transfer of protons, H+, from the acid to the base, leading to the formation of a neutral product. The general equation for neutralization is acid plus base salt plus water. For example, when hydrochloric acid, HCl, an acid, reacts with sodium hydroxide, NaOH, a base, the following neutralization reaction occurs. HCl plus NaOH NaCl plus H2O. In this reaction, the hydrogen ions from the acid combine with the hydroxide ions from the base to form water, H2O, while the sodium ion, Na+, from the base combines with the chloride ion, Cl, from the acid to form sodium chloride, NaCl, which is a salt. Neutralization reactions have important applications, such as. Let's define the following terms related to acids, bases, and oxides. 1. Acid. An acid is a substance that, when dissolved in water, releases hydrogen ions, H+. Acids have a sour taste, turn blue litmus paper red, and can react with bases to form salts and water in a neutralization reaction. 2. Acid anhydride. An acid anhydride is a nonmetal oxide that reacts with water to form an acid. They are formed by removing water from an acid. For example, sulfur trioxide, SO3, is the acid anhydride of sulfuric acid, H2SO4. 3. Base. A base is a substance that, when dissolved in water, releases hydroxide ions, OH. Bases have a bitter taste, feel slippery or soapy to the touch, turn red litmus paper blue, and can react with acids in a neutralization reaction. 4. Alkali. An alkali refers to a soluble base that releases hydroxide ions, OH, when dissolved in water. Sodium hydroxide, NaOH, and potassium hydroxide, KOH, are common examples of alkalis. 5. Salt. In chemistry, a salt refers to a compound formed by the reaction of an acid with a base. Salts are usually ionic compounds composed of positive ions, cations, from a base and negative ions, anions, from an acid. For example, sodium chloride, NaCl, is formed from the neutralization of hydrochloric acid, HCl, with sodium hydroxide, NaOH. 6. Acidic oxide. An acidic oxide is an oxide that, when dissolved in water, forms an acid. Acidic oxides typically react with water to produce hydrogen ions, H+, which make the solution acidic. For example, carbon dioxide, CO2, is an acidic oxide that dissolves in water to form carbonic acid, H2CO3. 7. Basic oxide. A basic oxide is an oxide that, when dissolved in water, forms a base. Basic oxides typically react with water to produce hydroxide ions, OH, which make the solution basic. For example, sodium oxide, Na2O, is a basic oxide that reacts with water to form sodium hydroxide, NaOH. 8. Amphoteric. Amphoteric substances can act as both acids and bases depending on the conditions. They can donate or accept protons depending on the nature of the other substance they are reacting with. An example of an amphoteric substance is water, H2O, which can act as an acid by donating a proton, H+, or as a base by accepting a proton. 9. Neutral oxide. A neutral oxide is an oxide that does not show significant acidic or basic properties when dissolved in water. Neutral oxides do not react with water to produce ions that affect the pH. An example of a neutral oxide is carbon monoxide, CO. These definitions should provide you with a good understanding of these terms related to acids, bases, and oxides. Acidity and alkalinity are directly related to the pH scale, which is a numerical scale used to measure the acidity or alkalinity of a solution. The pH scale ranges from 0 to 14, with 7 being considered neutral. pH values below 7. When the pH value of a solution is below 7, it indicates acidity. The lower the pH value, the more acidic the solution. A pH of 1 is highly acidic, while a pH of 6 is moderately acidic. pH values above 7. When the pH value of a solution is above 7, it indicates alkalinity, basicity. The higher the pH value, the more alkaline the solution. A pH of 13 is highly alkaline, while a pH of 8 is moderately alkaline. pH value of 7. A pH value of exactly 7 indicates neutrality. A neutral solution has an equal concentration of hydrogen ions, H+, and hydroxide ions, OH, and is neither acidic nor alkaline. Pure water has a pH of 7 and is considered neutral. The pH scale is logarithmic, meaning that each unit represents a tenfold difference in acidity or alkalinity. For example, a solution with a pH of 3 is 10 times more acidic than a solution with a pH of 4. The pH scale provides a quantitative measure of the concentration of hydrogen ions, H+, in a solution. Acids have a higher concentration of H+ ions, which results in a lower pH value, while bases have a higher concentration of hydroxide ions, OH, and a higher pH value. Understanding the pH scale allows us to determine the relative acidity or alkalinity of a solution and provides valuable information for various scientific, industrial, and everyday applications, such as monitoring water quality, adjusting pH in chemical reactions, and maintaining the pH balance in biological systems. The strength of acids and alkalis refers to their ability to undergo ionization in water, resulting in the formation of ions. The strength is determined by the extent of ionization, which relates to the completeness of ionization. 1. Acids. Strong acids. Strong acids completely ionize in water, meaning that nearly all the acid molecules dissociate into hydrogen ions, H+, and anions. Examples of strong acids include hydrochloric acid, HCl, sulfuric acid, H2SO4, and nitric acid, HNO3. Weak acids. Weak acids only partially ionize in water, resulting in a lower concentration of hydrogen ions. This means that not all acid molecules dissociate. Examples of weak acids include acetic acid, CH3COOH, carbonic acid, H2CO3, and citric acid, C6H8O7. 2. Alkalis, bases. Strong alkalis. Strong alkalis, also known as strong bases, fully dissociate in water, releasing a high concentration of hydroxide ions, OH. Examples of strong alkalis include sodium hydroxide, NaOH, potassium hydroxide, KOH, and calcium hydroxide, CaOH2. Weak alkalis. Weak alkalis only partially dissociate in water, resulting in a lower concentration of hydroxide ions. Examples of weak alkalis include ammonia, NH3, and aluminum hydroxide, AlOH3. The strength of an acid or alkali is related to its ability to donate or accept ions. Strong acids and alkalis readily donate or accept ions, leading to a high concentration of ions in solution. Weak acids and alkalis, on the other hand, have a lower tendency to donate or accept ions, resulting in a lower concentration of ions in solution. It's important to note that the strength of an acid or alkali is independent of its concentration. Concentration refers to the amount of acid or alkali in a given volume of solution, while strength relates to the extent of ionization. For example, a dilute solution of a strong acid can still be strong, as it undergoes complete ionization, whereas a concentrated solution of a weak acid will still be weak, as it only partially ionizes. Understanding the strength of acids and alkalis is crucial in various applications, such as chemical reactions, pH control, and understanding the behavior of substances in aqueous solutions. Non-oxidizing acids are acids that do not undergo oxidation reduction, Redox, reactions. These acids primarily donate hydrogen ions, H+, when dissolved in water, resulting in the formation of hydronium ions, H3O+. Let's investigate the reactions of non-oxidizing acids. 1. Reactions with metals. Non-oxidizing acids can react with certain metals to produce hydrogen gas and a corresponding metal salt. The general reaction is as follows. Non-oxidizing acid plus metal salt plus hydrogen gas. For example, when hydrochloric acid, HCl, reacts with zinc, Zn, the reaction can be represented as 2HCl plus Zn ZnCl2 plus H2. Here, zinc displaces hydrogen from hydrochloric acid, resulting in the formation of zinc chloride, ZnCl2, and hydrogen gas, H2. 2. Reactions with bases. Non-oxidizing acids can react with bases to form salts and water in a neutralization reaction. The general reaction is as follows. Non-oxidizing acid plus base salt plus water. For example, when sulfuric acid, H2SO4, reacts with sodium hydroxide, NaOH, the reaction can be represented as H2SO4 plus 2NaOH Na2SO4 plus 2H2O. Here, sulfuric acid reacts with sodium hydroxide to produce sodium sulfate, Na2SO4, and water, H2O. 3. Reactions with carbonates and bicarbonates. Non-oxidizing acids can react with carbonates, CO3-2, and bicarbonates, HCO3, to form carbon dioxide gas, water, and a corresponding salt. The general reaction is as follows. Non-oxidizing acid plus carbonate bicarbonate salt plus water plus carbon dioxide. For example, when hydrochloric acid, HCl, reacts with sodium bicarbonate, NaHCO3, the reaction can be represented as HCl plus NaHCO3 NaCl plus H2O plus CO2. Here, hydrochloric acid reacts with sodium bicarbonate to produce sodium chloride, NaCl, water, H2O, and carbon dioxide, CO2. These are some common reactions of non-oxidizing acids. It's important to note that the specific reactions may vary depending on the acid and the substance it reacts with. The reactions with non-oxidizing acids generally involve the formation of salts, water, and sometimes the release of carbon dioxide gas. Oxidation-reduction reactions, also known as redox reactions, involve the transfer of electrons between reactants. I can provide you with an explanation of oxidation and reduction and give you an example of a redox reaction. Here's what you need to know. 1. Oxidation. Oxidation is the process in which a substance loses electrons, increases its oxidation state, or gains oxygen. It is associated with the loss of hydrogen atoms or the addition of oxygen atoms. The substance undergoing oxidation is called the reducing agent or reductant. 2. Reduction. Reduction is the process in which a substance gains electrons, decreases its oxidation state, or loses oxygen. It is associated with the gain of hydrogen atoms or the loss of oxygen atoms. The substance undergoing reduction is called the oxidizing agent or oxidant. 3. Redox reaction. A redox reaction consists of both oxidation and reduction processes occurring simultaneously. In a redox reaction, one species gets oxidized, while another species gets reduced. The species being oxidized is the reducing agent, and the species being reduced is the oxidizing agent. Example of a redox reaction. Let's consider the reaction between magnesium, mg, and oxygen, O, to form magnesium oxide, mg O. The oxidation states of the elements involved are as follows, mg, 0, and O, -2. 2 megagrams plus O-2 mg O. In this reaction, magnesium, mg, is oxidized from an oxidation state of 0 to +2. Oxygen, O, is reduced from an oxidation state of 0 to -2. Hence, magnesium acts as the reducing agent, it undergoes oxidation, and oxygen acts as the oxidizing agent, it undergoes reduction, in this redox reaction. Please note that redox reactions can occur in various contexts, such as in the laboratory, industrial processes, or biological systems. The specific reaction conditions and species involved determine the nature and significance of the redox reaction. If you have any more specific questions or need further assistance, please let me know. Here are some common oxidizing and reducing substances that are involved in everyday activities. 1. Oxidizing substances. A. Bleach. Sodium hypochlorite bleach is commonly used as a household cleaner and disinfectant. It acts as an oxidizing agent, breaking down organic compounds and removing stains by oxidizing them. B. Hydrogen peroxide. HO hydrogen peroxide is used as an antiseptic, wound cleanser, and hair bleach. It releases oxygen when applied to wounds, aiding in the removal of debris and killing bacteria. C. Air. Oxygen in the air acts as an oxidizing agent in various processes, such as combustion, burning of fuels, rusting of metals, and spoilage of food. 2. Reducing substances. A. Antioxidants. Substances like vitamin C, vitamin E, and beta-carotene are antioxidants commonly found in fruits, vegetables, and other food sources. They help reduce oxidative stress by donating electrons and stabilizing free radicals in the body. B. Sodium bisulfite. NaHSO sodium bisulfite is often used as a food preservative, particularly in the preservation of fruits and vegetables. It acts as a reducing agent, preventing oxidation and the browning of produce. C. Hydrogen gas. Hydrogen gas can act as a reducing agent in various industrial processes. For example, it is used in the production of vegetable oils, where it helps remove impurities and reduce the levels of unsaturated fatty acids. These are just a few examples of common oxidizing and reducing substances and their applications in everyday activities. It's worth noting that the specific use and function of these substances can vary depending on the context and the desired outcome. If you have any more specific questions or need further information, feel free to ask. Here are the definitions of oxidation and reduction. 1. Oxidation. Oxidation is a chemical process in which a substance loses electrons, increases its oxidation state, or gains oxygen. It involves the transfer of electrons from one species to another. Oxidation is often accompanied by other observable changes, such as the loss of hydrogen atoms or the addition of oxygen atoms. Some key points about oxidation include: oxidation involves the loss of electrons. The substance undergoing oxidation is called the reducing agent or reductant. Oxidation leads to an increase in the oxidation state of the substance. 2. Reduction. Reduction is a chemical process in which a substance gains electrons, decreases its oxidation state, or loses oxygen. It also involves the transfer of electrons between species. Reduction is often accompanied by other observable changes, such as the gain of hydrogen atoms or the loss of oxygen atoms. Some key points about reduction include: reduction involves the gain of electrons. The substance undergoing reduction is called the oxidizing agent or oxidant. Reduction leads to a decrease in the oxidation state of the substance. Oxidation and reduction are complementary processes that occur simultaneously in a chemical reaction, known as a redox, oxidation-reduction, reaction. In a redox reaction, one species undergoes oxidation, while another species undergoes reduction. The species being oxidized is the reducing agent, and the species being reduced is the oxidizing agent. It's important to note that oxidation and reduction are defined based on the transfer of electrons and changes in oxidation states of substances involved in a reaction. These processes have widespread applications in various fields, including chemistry, biology, industry, and everyday life. If you have any further questions or need additional clarification, please let me know. To deduce the oxidation number from a formula, you need to understand the rules and guidelines for assigning oxidation numbers. Here are the steps to deduce the oxidation number from a formula. 1. Understand the concept of oxidation number. Oxidation number, also known as oxidation state, is a value assigned to an atom within a compound or ion to indicate the electron distribution or the apparent charge on the atom. 2. Familiarize yourself with the general guidelines for assigning oxidation numbers. The oxidation number of an uncombined element, example, NaON, is 0. The oxidation number of a monatomic ion is equal to its charge. For example, Na has an oxidation number of +1, while Cl has an oxidation number of -1. In most compounds, oxygen has an oxidation number of -2. Exceptions include peroxides, such as HO, where oxygen has an oxidation number of -1, and compounds like Of, where oxygen has an oxidation number of +2. Hydrogen usually has an oxidation number of +1 in compounds, except in metal hydrides, example, Na, where hydrogen has an oxidation number of -1. The sum of oxidation numbers in a neutral compound is 0, and in an ion, it is equal to the ion's charge. 3. Apply the guidelines to deduce the oxidation numbers. Start with elements that have a known or fixed oxidation number, such as alkali metals, +1, alkaline earth metals, +2, and halogens, -1. Use the overall charge of the compound or ion to determine the oxidation numbers of other elements. For example, in NaCl, the oxidation number of chlorine, -1, can be deduced based on the charge of the sodium ion, +1, and the overall charge neutrality of the compound, 0. Consider the rules for assigning oxidation numbers to specific elements based on their known behavior and typical oxidation states. For example, in compounds involving oxygen, oxygen is usually assigned an oxidation number of -2 unless it falls into an exception category, as mentioned earlier. Adjust the oxidation numbers of other elements to satisfy the charge requirements of the compound or ion. It's important to note that assigning oxidation numbers can sometimes be more complex in certain compounds or situations. However, these guidelines will help you deduce the oxidation numbers in most cases. If you have any specific compounds or examples in mind, feel free to provide them, and I can help you determine the oxidation numbers. I'll explain how to identify oxidation and reduction reactions, including reactions at electrodes. 1. Oxidation reaction. In an oxidation reaction, a substance loses electrons, increases its oxidation state, or gains oxygen. The oxidation state of the element or compound undergoing oxidation increases. For example, consider the reaction ZnS plus Cu squared, Ac, Zn squared, Ac, plus Cos. In this reaction, zinc, Zn, is oxidized from an oxidation state of 0 to +2, losing 2 electrons. Hence, it is the oxidation reaction. 2. Reduction reaction. In a reduction reaction, a substance gains electrons, decreases its oxidation state, or loses oxygen. The oxidation state of the element or compound undergoing reduction decreases. Using the same example as above. ZnS plus Cu squared, Ac, Zn squared, Ac, plus Cos. Copper, Cu squared, is reduced from an oxidation state of +2 to 0, gaining 2 electrons. Therefore, it is the reduction reaction. 3. Reactions at electrodes. Electrodes are conductive surfaces where oxidation and reduction reactions occur in electrochemical cells or electrolysis processes. At the anode, negative electrode, oxidation occurs, and electrons are released. It is where the reducing agent loses electrons. At the cathode, positive electrode, reduction occurs, and electrons are gained. It is where the oxidizing agent accepts electrons. For example, in the electrolysis of water. At the anode, 2HO, L, O, G, plus 4H, Ac, plus 4E. At the cathode, 4H, Ac, plus 4E2H, G. In this case, the anode reaction involves oxidation, loss of electrons, while the cathode reaction involves reduction, gain of electrons. By analyzing the changes in oxidation states and electron transfers, you can identify oxidation and reduction reactions, including those occurring at electrodes in electrochemical processes. If you have any specific reactions or further questions, feel free to ask. Distinguishing between oxidizing and reducing agents is important in understanding their roles in chemical reactions. Here's how you can differentiate between oxidizing and reducing agents. 1. Oxidizing agent. An oxidizing agent is a substance that causes oxidation in another substance by accepting electrons from it. It gets reduced itself, meaning it gains electrons during the reaction. Oxidizing agents are typically electron acceptors and are often characterized by having high electronegativity or high oxidation states. Examples of common oxidizing agents include oxygen, O, hydrogen peroxide, HO, chlorine, Cl, and potassium permanganate, KMNO. Oxidizing agents tend to be involved in reactions where they remove electrons from other species, causing them to be oxidized. 2. Reducing agent. A reducing agent is a substance that causes reduction in another substance by donating electrons to it. It gets oxidized itself, meaning it loses electrons during the reaction. Reducing agents are typically electron donors and are often characterized by having low electronegativity or low oxidation states. Examples of common reducing agents include hydrogen gas, H, carbon monoxide, CO, sodium borohydride, NaBH, and ferrous ion, Fe². Reducing agents tend to be involved in reactions where they provide electrons to other species, causing them to be reduced. To summarize, oxidizing agents accept electrons and get reduced. Reducing agents donate electrons and get oxidized. It's important to note that the distinction between oxidizing and reducing agents is relative to the specific reaction and the species involved. A substance can act as an oxidizing agent in one reaction and a reducing agent in another, depending on the context. Understanding the roles of oxidizing and reducing agents is fundamental in redox reactions and helps in predicting reaction outcomes, identifying reaction mechanisms, and explaining the behavior of various compounds. If you have any further questions, feel free to ask. Here are some tests you can perform to identify oxidizing and reducing agents. 1. Test for oxidizing agents. One common test to identify oxidizing agents is the reaction with a reducing agent. The oxidizing agent will oxidize the reducing agent, resulting in a visible change or reaction. Here's an example. A. Test with potassium iodide, Ki, solution. Add a small amount of the suspected oxidizing agent to a solution of potassium iodide, Ki, in water. If the solution turns brown or yellow, it indicates the presence of an oxidizing agent. The oxidizing agent oxidizes iodide ions, I, to form iodine, I, which imparts a brown color to the solution. 2. Test for reducing agents. A common test to identify reducing agents is the reaction with an oxidizing agent. The reducing agent will reduce the oxidizing agent, resulting in a visible change or reaction. Here's an example. A. Test with acidified potassium manganate, 7, KMnO, solution. Add a small amount of the suspected reducing agent to a solution of acidified potassium manganate, 7, KMnO. If the purple color of KMnO solution fades or changes to colorless, it indicates the presence of a reducing agent. The reducing agent reduces the Mn, 7, ions in KMnO to Mn, 2, ions, causing the color change. These are just a couple of examples of tests for oxidizing and reducing agents. Depending on the specific oxidizing or reducing agent you want to test, there may be other specific tests or methods available. It's also important to exercise caution and follow proper safety protocols when performing any chemical tests. Remember, the results of these tests will depend on the specific substances being tested and their reactivity with the oxidizing or reducing agent. It's always recommended to consult appropriate references or perform tests under the guidance of an experienced chemist. If you have any more specific questions or need further assistance, feel free to ask. Let's delve into the topic of electrochemistry. Here's an overview of key concepts in electrochemistry. 1. Electrochemical cells. Electrochemical cells are devices that convert chemical energy into electrical energy or vice versa through redox reactions. They consist of two electrodes, anode and cathode, immersed in an electrolyte solution. There are two types of electrochemical cells, galvanic, voltaic, cells and electrolytic cells. 2. Galvanic cells, voltaic cells. Galvanic cells are spontaneous electrochemical cells that generate electrical energy from a spontaneous redox reaction. They have a positive cell potential, ECL, and produce an electric current that flows from the anode, site of oxidation, to the cathode, site of reduction. Examples of galvanic cells include batteries and fuel cells. 3. Electrolytic cells. Electrolytic cells are non-spontaneous electrochemical cells that require an external source of electrical energy to drive a non-spontaneous redox reaction. They have a negative cell potential, ECL, and use electrical energy to facilitate the redox reaction. Electrolytic cells are used for processes like electroplating, electrolysis of water, and metal extraction. 4. Oxidation and reduction at electrodes. At the anode, negative electrode, oxidation occurs, and electrons are released. The anode is labeled dash in an electrochemical cell. At the cathode, positive electrode, reduction occurs, and electrons are gained. The cathode is labeled plus in an electrochemical cell. 5. Electrochemical notation. Electrochemical cells are represented using cell notation, which consists of the anode, cathode, and salt bridge separated by vertical lines. For example, in a ZnCu galvanic cell, the cell notation would be ZnS Zn squared, Ac, Cu squared, Ac, cos. 6. Standard electrode potential. Standard electrode potential, E degree, is a measure of the tendency of a substance to gain or lose electrons compared to a standard hydrogen electrode, SHE. E degree values indicate the relative strengths of oxidizing and reducing agents. Positive E degree values indicate a substance acts as an oxidizing agent, while negative E degree values indicate a substance acts as a reducing agent. These are some fundamental concepts in electrochemistry. The field of electrochemistry has applications in various areas, including energy storage, corrosion prevention, electroplating, and electrolysis processes. If you have specific questions or need more information on any subtopic within electrochemistry, feel free to ask. Here's a guideline for conducting investigations to classify substances as conductors or non-conductors. 1. Gather materials. Various substances to test, example, metals, nonmetals, liquids, solids. Power source, example, batteries, power supply. Wires with alligator clips or conductivity tester. Light bulb or buzzer, optional. 2. Set up the experiment. Create a simple circuit by connecting the power source to the wires or conductivity tester. Ensure the circuit is complete by connecting the wires or tester to form a closed loop. If using a light bulb or buzzer, connect it in series with the circuit to detect the flow of electric current. 3. Perform the tests. Begin with a known conductor, such as a metal, example, copper wire. Attach the wire to the circuit and observe if the light bulb illuminates or the buzzer sounds. This confirms that the circuit is functioning correctly. Move on to test the substances you wish to classify. Hold one end of the substance with an alligator clip and attach the other end to the circuit. Observe if there is any change in the light bulb or buzzer. If the light bulb illuminates or the buzzer sounds, the substance is a conductor of electricity. If there is no change in the light bulb or buzzer, the substance is a non-conductor, insulator, of electricity. 4. Record and analyze the results. Note down your observations for each substance tested, classifying them as conductors or non-conductors. Compare the substances and look for patterns or trends. For example, metals are generally good conductors, while most non-metals and insulating materials are poor conductors. Consider the chemical and physical properties of the substances that may influence their conductivity, such as their atomic structure, presence of free electrons, and ability to form ions. 5. Repeat and refine. Repeat the tests for accuracy and consistency. If necessary, refine the experiment by using different types of substances, adjusting the circuit setup, or exploring other conductivity testing methods, example, using a conductivity meter. By conducting these investigations and classifying substances as conductors or non-conductors, you can gain a better understanding of the electrical properties of different materials. This knowledge has practical applications in fields such as electrical engineering, materials science, and circuit design. Remember to exercise caution and follow safety guidelines when working with electricity and conducting experiments. If you have any further questions or need additional assistance, feel free to ask. Distinguishing between metallic and electrolytic conduction involves understanding the key differences in how electrical conduction occurs in metals and electrolytes. Here's a comparison between metallic and electrolytic conduction. 1. Metallic conduction. Metallic conduction occurs in metals and is the result of the movement of free electrons. Metals have a lattice structure of positively charged metal ions in a sea of delocalized electrons. When a voltage is applied across a metal, the free electrons can move in response to the electric field, creating an electric current. The mobility of the free electrons in metals allows for efficient and rapid conduction of electricity. Examples of metallic conduction include the flow of electricity through a copper wire or the conduction of electric current in a metal electrode. 2. Electrolytic conduction. Electrolytic conduction occurs in electrolytes, which are substances that conduct electricity when dissolved in a solvent, usually water, or in molten form. Electrolytes are typically ionic compounds that dissociate into positive and negative ions when dissolved or melted. When a voltage is applied across an electrolyte solution or molten electrolyte, the positively charged ions, cations, are attracted to the negative electrode, cathode, while the negatively charged ions, anions, are attracted to the positive electrode, anode. The movement of ions toward the electrodes allows for the flow of electric current through the electrolyte. Examples of electrolytic conduction include the conduction of electricity in solutions containing electrolytes, such as in a saltwater solution or during electrolysis processes. Key differences. Metallic conduction involves the movement of free electrons, while electrolytic conduction involves the movement of ions. Metallic conduction occurs in solid metals, while electrolytic conduction can occur in solutions or molten electrolytes. Metallic conduction is characterized by the presence of a sea of delocalized electrons in metals, while electrolytic conduction involves the migration of ions in an electrolyte. It's important to note that metallic and electrolytic conduction are distinct processes, each governed by their specific mechanisms. However, both types of conduction are vital in various fields, including electronics, electrochemistry, and materials science. If you have any further questions or need additional clarification, feel free to ask. Electrolytes can be classified as strong or weak based on their conductivity, which reflects their ability to dissociate into ions in solution. Here's how you can classify electrolytes as strong or weak. 1. Strong electrolytes. Strong electrolytes are substances that completely dissociate into ions when dissolved in water or molten form. They conduct electricity very effectively due to the high concentration of ions. Strong acids, strong bases, and soluble salts are examples of strong electrolytes. Strong acids, such as hydrochloric acid, HCl, or sulfuric acid, HSO, fully ionize in water to release hydrogen ions, H. Strong bases, such as sodium hydroxide, NaOH, or potassium hydroxide, KOH, dissociate completely in water to produce hydroxide ions, O. Soluble salts, like sodium chloride, NaCl, or potassium nitrate, NO, readily dissolve in water and dissociate into cations and anions. 2. Weak electrolytes. Weak electrolytes are substances that only partially dissociate into ions when dissolved in water or molten form. They conduct electricity to a lesser extent compared to strong electrolytes due to a lower concentration of ions. Weak acids, weak bases, and some salts are examples of weak electrolytes. Weak acids, such as acetic acid, CHCOOH, or carbonic acid, HCO, dissociate partially in water, resulting in a lower concentration of hydrogen ions. Weak bases, such as ammonia, NH, or ammonium hydroxide, NHO, also partially dissociate in water, yielding a lower concentration of hydroxide ions. Some salts, like copper sulfate, CuSO, or calcium carbonate, CaCO, exhibit partial ionization in water. To classify an electrolyte as strong or weak based on its conductivity, you can perform a simple conductivity test. By measuring the electrical conductivity of a solution of the electrolyte, you can determine its dissociation level and thus its strength as an electrolyte. Strong electrolytes will exhibit high conductivity, while weak electrolytes will show lower conductivity. It's important to note that the classification of electrolytes as strong or weak is based on their behavior in aqueous solutions or molten form. The strength of an electrolyte can also be represented by its dissociation constant, Ka or Kb, or by the degree of ionization. If you have any further questions or need additional clarification, feel free to ask. Here are the definitions of electrolysis: cathode, anode, cation, and anion. 1. Electrolysis. Electrolysis refers to a process in which an electric current is used to drive a non-spontaneous chemical reaction. It involves the decomposition of an electrolyte, a compound that conducts electricity when dissolved in a solvent or in molten form, into its constituent ions. 2. Cathode. The cathode is an electrode in an electrochemical cell or electrolytic cell where reduction, gain of electrons, takes place. During electrolysis, positive ions, cations, in the electrolyte are attracted to the cathode, where they gain electrons and undergo reduction. The cathode is labeled plus in a galvanic cell, where spontaneous oxidation-reduction reactions occur, and dash in an electrolytic cell, where non-spontaneous reactions occur. 3. Anode. The anode is an electrode in an electrochemical cell or electrolytic cell where oxidation, loss of electrons, takes place. During electrolysis, negative ions, anions, in the electrolyte are attracted to the anode, where they lose electrons and undergo oxidation. The anode is labeled dash in a galvanic cell and plus in an electrolytic cell. 4. Cation. A cation is a positively charged ion that is formed when an atom or a molecule loses one or more electrons. Cations are attracted to the cathode during electrolysis and undergo reduction. Examples of cations include H, hydrogen ion, Na, sodium ion, and mg², magnesium ion. 5. Anion. An anion is a negatively charged ion that is formed when an atom or a molecule gains one or more electrons. Anions are attracted to the anode during electrolysis and undergo oxidation. Examples of anions include Cl, chloride ion, O, hydroxide ion, and SO2, sulfate ion. These terms are fundamental to understanding the principles of electrolysis and electrochemistry. Electrolysis has numerous applications, such as electroplating, metal extraction, water electrolysis, and electrolytic refining. If you have any further questions or need additional clarification, feel free to ask. To identify the ions present in electrolytes, you need to consider the chemical formula of the electrolyte and determine the ions it dissociates into when dissolved in a solvent, usually water, or in molten form. Here's a general approach to identifying ions in electrolytes. 1. Determine the chemical formula. Start by knowing the chemical formula of the electrolyte you are investigating. For example, if you have an electrolyte such as NaCl, the chemical formula indicates that it contains sodium, Na, and chloride, Cl, ions. 2. Consider the ionic nature of the electrolyte. Electrolytes are typically ionic compounds that dissociate into positive, cations, and negative, anions, ions when dissolved or molten. Some common examples of electrolytes include salts, acids, and bases. 3. Identify cations. Look for elements that tend to lose electrons to form positive ions, cations. Examples of common cations include Na, sodium, K, potassium, mg², magnesium, and Ca², calcium. The cations are typically derived from metals or positively charged polyatomic ions. 4. Identify anions. Look for elements or groups of atoms that tend to gain electrons to form negative ions, anions. Examples of common anions include Cl, chloride, SO2, sulfate, O, hydroxide, and No, nitrate. The anions can be derived from nonmetals or negatively charged polyatomic ions. 5. Consider solubility rules, if applicable. In some cases, the solubility of the electrolyte may affect the presence of specific ions in solution. Solubility rules provide guidelines for determining the solubility of various compounds and the resulting ions. For example, if you have a compound like AgCl, silver chloride, it is insoluble in water, so the Ag and Cl ions would not be present in significant amounts in the solution. 6. Use reference materials. Reference materials, such as chemistry textbooks or online resources, can provide specific information on the ions present in different electrolytes. Periodic tables and chemical databases can also help determine the charges and identities of common ions. By considering the chemical formula, the ionic nature of the electrolyte, and applying knowledge of cations and anions, you can identify the ions present in electrolytes. It's important to note that the identification of ions may also depend on factors such as concentration, pH, and temperature. If you have a specific electrolyte in mind or need assistance with identifying ions in a particular compound, please provide more details, and I'll be happy to help further. To predict the electrode to which an ion will drift during electrolysis, you need to consider the charge of the ion and the electrode potentials. Here's a general approach to predicting the electrode to which an ion will drift. 1. Determine the charge of the ion. Identify the charge of the ion in the electrolyte. Positive ions, cations, have a net positive charge, while negative ions, anions, have a net negative charge. For example, in the electrolyte NaCl, the sodium ion, Na, is a cation with a positive charge, and the chloride ion, Cl, is an anion with a negative charge. 2. Understand electrode potentials. Electrode potentials represent the tendency of an electrode to gain or lose electrons during an electrochemical reaction. Each electrode has a specific potential measured with respect to a reference electrode, usually a standard hydrogen electrode. The electrode potential can be either positive or negative, depending on the tendency of the electrode to gain or lose electrons. 3. Apply the general rule. Positive ions, cations, are attracted to the negative electrode, cathode, while negative ions, anions, are attracted to the positive electrode, anode. Cations, which have a positive charge, move toward the negative electrode, cathode, to gain electrons and undergo reduction. Anions, which have a negative charge, move toward the positive electrode, anode, to lose electrons and undergo oxidation. 4. Consider exceptions. There may be exceptions to the general rule based on specific electrochemical reactions or factors such as concentration, temperature, and pH. For example, in some cases, the presence of certain ions or the solubility of specific compounds can affect the behavior of ions during electrolysis. It's important to note that the prediction of ion drift during electrolysis is based on general principles and may vary depending on the specific electrolyte and experimental conditions. Factors such as the applied voltage, concentration of ions, and presence of competing reactions can also influence the ion migration. If you have a specific electrolyte or ion in mind, or need further assistance with predicting the electrode to which an ion will drift, please provide more details, and I'll be happy to help. To predict chemical reactions using the electrochemical series, you can compare the relative positions of different elements or ions in the series. The electrochemical series, also known as the activity series or electromotive series, ranks elements and ions based on their tendency to undergo oxidation or reduction reactions. Here's how you can use the electrochemical series to predict chemical reactions. 1. Understand the electrochemical series. The electrochemical series ranks elements and ions based on their standard electrode potentials, E degree. Elements or ions higher in the series have a greater tendency to undergo reduction, gain electrons, and act as oxidizing agents. Elements or ions lower in the series have a greater tendency to undergo oxidation, lose electrons, and act as reducing agents. 2. Compare the positions of elements ions. When predicting chemical reactions, compare the positions of the relevant elements or ions in the electrochemical series. A higher-ranked element ion will oxidize a lower-ranked element ion if they come into contact, leading to a spontaneous redox reaction. 3. Predict the direction of the reaction. If the element or ion higher in the series is above the other in the series, it will act as the oxidizing agent and undergo reduction. The element or ion lower in the series will act as the reducing agent and undergo oxidation. The oxidizing agent gains electrons and is reduced, while the reducing agent loses electrons and is oxidized. 4. Write the balanced redox reaction. Write the balanced equation for the redox reaction, ensuring that the number of electrons lost by the reducing agent equals the number of electrons gained by the oxidizing agent. Include the appropriate stoichiometric coefficients to balance the reaction. 5. Consider additional factors. Other factors, such as concentration, temperature, and pH, can also influence the occurrence and direction of redox reactions, even if the electrochemical series predicts a potential reaction. These factors may lead to exceptions or modifications in the predicted reactions. By using the electrochemical series, you can predict the feasibility and direction of redox reactions between different elements or ions. The series is a useful tool for understanding the relative strength of oxidizing and reducing agents. It's important to note that the electrochemical series provides a general guideline, and actual experimental conditions and specific reactions may have additional factors to consider. Additionally, the electrochemical series typically applies to aqueous solutions under standard conditions. If you have a specific reaction or need assistance with predicting a particular redox reaction using the electrochemical series, please provide more details, and I'll be happy to help. Here is a discussion of the electrolysis of certain substances. 1. Electrolysis of water, H2O. When water is electrolyzed, it undergoes decomposition into hydrogen gas, H2, and oxygen gas, O2. The electrolysis of water occurs in an electrolytic cell with two electrodes, a positive electrode, anode, and a negative electrode, cathode. At the cathode, water is reduced, and hydrogen gas is produced, 2H2O, L, plus 2EH2, G, plus 2OH. At the anode, water is oxidized, and oxygen gas is produced, 4OHO2, G, plus 2H2O, L, plus 4E. Overall reaction, 2H2O, L, 2H2, G, plus O2, G. 2. Electrolysis of sodium chloride, NaCl. Electrolysis of a sodium chloride solution, brine, can produce chlorine gas, Cl2, hydrogen gas, H2, and sodium hydroxide, NaOH. The electrolysis occurs in an electrolytic cell with two electrodes, a positive electrode, anode, and a negative electrode, cathode. At the cathode, water is reduced, and hydrogen gas is produced, 2H2O, L, plus 2EH2, G, plus 2OH. At the anode, chloride ions, Cl, are oxidized, and chlorine gas is produced, 2Cl, Cl2, G, plus 2E. The sodium ions, Na+, and hydroxide ions, OH, remain in the solution, forming sodium hydroxide, NaOH. 3. Electrolysis of copper sulfate, CuSO4. Electrolysis of a copper sulfate solution can be used to electroplate copper onto a conducting surface or purify copper. The electrolysis occurs in an electrolytic cell with two electrodes, a positive electrode, anode, and a negative electrode, cathode. At the cathode, copper ions, Cu2+, from the copper sulfate solution are reduced, and solid copper is deposited, Cu2++ 2E, Cos. At the anode, the copper anode is oxidized, releasing copper ions into the solution, Cos-Cu2++ 2E. Overall, copper is transferred from the anode to the cathode, leading to the plating or purification of copper. These examples highlight some common electrolysis reactions. The specific products and reactions in electrolysis depend on the nature of the electrolyte, concentration, and experimental conditions. It's important to note that during electrolysis, oxidation occurs at the anode, while reduction occurs at the cathode. If you have any more specific questions or need further information on electrolysis reactions, feel free to ask. The Faraday constant is a fundamental constant in electrochemistry that relates the amount of electric charge passed during an electrolysis process to the amount of substance being transformed at the electrode. It is named after the English scientist Michael Faraday, who made significant contributions to the field of electromagnetism. The Faraday constant, F, is defined as the electric charge carried by 1 mole of electrons and is approximately equal to 96,485 coulombs per mole, C-mole. The value of the Faraday constant can be expressed in different units, such as joules per volt per mole, JV mole, or farads per mole, F mole. Mathematically, the Faraday constant can be represented as F equals N times E, where F is the Faraday constant, N is Avogadro's number, approximately 6.022 times 10 to the power of 23 mol to the power of 1. E is the elementary charge, approximately 1.602 times 10 to the power of 1 C. The Faraday constant plays a crucial role in various electrochemical calculations and equations. It is used to determine the amount of substance undergoing electrolysis based on the quantity of electric charge passed. It also relates the current, in amperes, in an electrochemical cell to the amount of substance being transformed at the electrodes. The Faraday constant allows scientists and engineers to make quantitative connections between the flow of electricity and the amount of chemical reactions occurring during electrolysis or other electrochemical processes. If you have any further questions or need additional clarification, feel free to ask. To calculate the masses and volumes of substances liberated during electrolysis, you need to consider the stoichiometry of the chemical reaction and Faraday's laws of electrolysis. Here's a general approach to calculate the masses and volumes of substances liberated. 1. Determine the balanced chemical equation. Start by writing the balanced chemical equation for the electrolysis reaction. The equation should show the reactants, the products formed, and the number of moles of each substance involved in the reaction. 2. Identify the stoichiometry of the reaction. Examine the balanced equation to determine the mole ratios between the substances involved in the reaction. These ratios will help you convert between moles of reactants products and calculate the quantities of substances liberated. 3. Apply Faraday's laws of electrolysis. Faraday's first law states that the amount of substance liberated during electrolysis is directly proportional to the quantity of electricity passed through the cell. Faraday's second law states that the amount of different substances liberated by the same quantity of electricity is proportional to their respective chemical equivalent weights. 4. Calculate the quantity of electricity. Use the formula Q equals I times T to calculate the quantity of electricity passed, where Q is the charge in coulombs, C, I is the current in amperes, A, and T is the time in seconds, S. 5. Convert coulombs to moles. Apply Faraday's constant, F, to convert the quantity of electricity in coulombs to moles of electrons. Moles of electrons equals Q, F times N, where N is the number of electrons involved in the balanced equation for the reaction. 6. Calculate the moles of substances liberated. Use the mole ratios from the balanced equation to determine the moles of substances liberated. Multiply the moles of electrons by the stoichiometric coefficients of the substances in the balanced equation. 7. Convert moles to mass or volume. Convert the moles of substances liberated to their corresponding mass or volume. Use the molar mass of the substance to convert moles to mass, or use the molar volume at standard conditions to convert moles to volume. 8. Perform unit conversions. Apply appropriate unit conversions to obtain the desired units for mass or volume, example, grams, liters, milliliters, etc. Remember, the specific calculations will depend on the electrolysis reaction and the substances involved. It's essential to use accurate molar masses and consult reliable sources for molar volumes. If you have a specific electrolysis reaction or need help with a particular calculation, please provide more details, and I'll be happy to assist you further. Electrolysis has several important industrial applications across various sectors. Here are some notable examples. 1. Electroplating. Electroplating is a widely used industrial application of electrolysis. It involves the deposition of a layer of metal onto a surface to enhance its appearance, provide protection, or modify its properties. Common applications of electroplating include coating objects with gold, silver, nickel, chromium, or other metals. This process is employed in jewelry manufacturing, automotive industry, chrome plating, electronics industry, and many other sectors. 2. Electrorefining of metals. Electrorefining is the process of purifying metals through electrolysis. It is commonly used in the refining of copper, zinc, and other metals. In copper electrorefining, impure copper is used as an anode, and pure copper is deposited on the cathode. This process helps remove impurities and produce high-quality copper suitable for various applications, including electrical wiring, plumbing, and industrial machinery. 3. Production of sodium hydroxide and chlorine. The electrolysis of brine, a solution of sodium chloride, is used to produce sodium hydroxide, NaOH, and chlorine gas, Cl2, on an industrial scale. In this process, called chloralkali electrolysis, sodium ions, Na+, are reduced to form sodium hydroxide at the cathode, while chloride ions, Cl, are oxidized to form chlorine gas at the anode. Sodium hydroxide finds applications in industries such as pulp and paper, textiles, water treatment, and chemical manufacturing. Chlorine is used for various purposes, including water disinfection, production of PVC, and manufacturing of various chemicals. 4. Electrolytic production of aluminum. The Hall-Héroult process is an important industrial application of electrolysis used for the production of aluminum from aluminum oxide, Al2O3. In this process, aluminum oxide is dissolved in a molten mixture of cryolite, Na3Al6, and other compounds. The mixture is electrolyzed, with carbon electrodes used as the anode and a cathode. The electrolysis of aluminum oxide results in the production of pure molten aluminum at the cathode, which can be further processed into aluminum products. This process is energy-intensive but crucial for the production of aluminum, widely used in construction, transportation, packaging, and other industries. 5. Electrolytic refining of gold and silver. Electrolysis is used in the refining of precious metals like gold and silver. In this process, impure gold or silver is used as the anode, and pure gold or silver is deposited on the cathode. Electrolysis helps remove impurities and achieve high levels of purity in these valuable metals, which are used in jewelry, electronics, and investment. These are just a few examples of the industrial applications of electrolysis. Electrolysis plays a significant role in various other sectors, including chemical manufacturing, energy storage, metal recycling, and more. It enables the production of specific chemicals, the purification of metals, and the modification of material properties to meet industrial requirements. Here are some key points related to the topic of rates of reaction. 1. Definition of reaction rate. The rate of reaction refers to how quickly a chemical reaction takes place and is a measure of the change in concentration of reactants or products per unit time. It is usually expressed as the change in concentration, or amount, of a substance over a specified time interval. 2. Factors affecting reaction rate. Concentration. Increasing the concentration of reactants generally leads to an increase in the reaction rate as there are more particles available for collisions. Temperature. Higher temperatures usually result in faster reaction rates as particles have more kinetic energy, leading to more frequent and energetic collisions. Surface area. Increasing the surface area of solid reactants can accelerate the reaction rate by exposing more particles to the other reactants, promoting collisions. Catalysts. Catalysts are substances that increase the rate of a chemical reaction by providing an alternative reaction pathway with lower activation energy. Pressure. For gaseous reactions, increasing the pressure for gaseous reactions involving reactant gases can enhance reaction rates by compressing the particles and increasing the frequency of collisions. 3. Reaction rate and collision theory. The collision theory states that for a chemical reaction to occur, reactant particles must collide with sufficient energy and proper orientation. Effective collisions possess enough energy to overcome the activation energy barrier and result in the formation of products. 4. Reaction rate equation. The rate of a chemical reaction is often expressed using the rate equation or rate law, which relates the reaction rate to the concentrations of the reactants. The rate equation typically takes the form, rate equals K, A, caret M, B, caret N, where A and B represent the concentrations of the reactants, and K is the rate constant. 5. Reaction mechanisms and rate determining steps. Many reactions occur through a series of individual steps known as the reaction mechanism. The rate-determining step is the slowest step in the reaction mechanism and determines the overall rate of the reaction. 6. Methods to measure reaction rate. Several experimental techniques can be employed to measure reaction rates, such as monitoring changes in concentration using spectrophotometry, titration, or gas volume measurements. The initial rate method involves measuring the change in concentration of reactants or products over a short time interval at the beginning of the reaction. 7. Rate laws and reaction order. The rate law describes the mathematical relationship between the rate of a reaction and the concentrations of the reactants. The reaction order refers to the power to which the concentration of a reactant is raised in the rate law equation. Understanding the rates of chemical reactions is crucial for various fields, including chemical engineering, pharmaceuticals, environmental science, and more. By studying the factors that influence reaction rates, scientists and engineers can optimize reaction conditions, design efficient processes, and develop new technologies. If you have any specific questions or need further information on rates of reaction, feel free to ask. The rate of reaction is a measure of how quickly a chemical reaction takes place. It quantifies the change in concentration of reactants or products over a specific time period. The rate of reaction indicates the speed at which reactant particles are transformed into product particles. The rate of reaction can be expressed in terms of the change in concentration of a reactant or product per unit time. It is typically represented as rate of reaction equals A, T or B, T, where A and B represent the concentrations of reactants A and B, respectively. A and B represent the change in concentration of reactants A and B over a specific time interval T. The rate of reaction can also be expressed in terms of the disappearance of reactants or the appearance of products. For example, if reactant A is consumed during the reaction, the rate of reaction can be expressed as rate of reaction equals A, T. The negative sign indicates the decrease in concentration of reactant A over time. It's important to note that the rate of reaction is influenced by various factors such as reactant concentration, temperature, surface area, presence of catalysts, and pressure, for gaseous reactions. By studying the rate of reaction and its dependence on these factors, scientists can gain insights into the underlying mechanisms and kinetics of chemical reactions. If you have any more specific questions or need further clarification, feel free to ask. Several factors can affect the rate of a chemical reaction. Here are the key factors that influence the rate of reaction. 1. Concentration of reactants. The concentration of reactants plays a significant role in determining the rate of reaction. Increasing the concentration of reactants generally leads to an increase in the rate of reaction. Higher concentrations provide more particles per unit volume, resulting in a higher frequency of collisions and a greater chance of successful collisions. 2. Temperature. Temperature has a direct effect on the rate of reaction. Increasing the temperature generally increases the rate of reaction. Higher temperatures provide reactant particles with more kinetic energy, resulting in faster movement and more frequent collisions with sufficient energy to overcome the activation energy barrier. 3. Surface area. The surface area of solid reactants influences the rate of reaction. A larger surface area leads to increased contact between reactant particles and other reactants, facilitating more collisions and higher reaction rates. Grinding or dividing a solid reactant into smaller particles can increase the surface area and thus accelerate the reaction. 4. Pressure, for gaseous reactions. Pressure affects the rate of gaseous reactions. Increasing the pressure of gaseous reactants typically increases the rate of reaction. Higher pressures result in a greater number of gas particles per unit volume, leading to more frequent collisions and increased reaction rates. 5. Catalysts. Catalysts are substances that increase the rate of a chemical reaction without being consumed in the process. Catalysts provide an alternative reaction pathway with a lower activation energy, allowing more reactant particles to overcome the energy barrier and proceed with the reaction. The presence of a catalyst can significantly speed up a reaction and enhance the rate. 6. Nature of reactants. The nature and composition of the reactants can influence the rate of reaction. Different substances have different chemical properties and reactivity. For example, reactions involving highly reactive substances or substances with strong bonds may exhibit faster rates compared to reactions involving less reactive substances or substances with weaker bonds. It's important to note that these factors affect the rate of reaction by influencing the frequency of collisions, the energy of collisions, or both. By controlling these factors, scientists and engineers can optimize reaction conditions, increase reaction rates, and design more efficient processes. If you have any more questions or need further clarification, feel free to ask. To predict the effect of factors on rates of reaction from given data, you can analyze the relationship between the factors and the observed reaction rates. Here's a general approach. 1. Gather data. Collect data on the reaction rates under different conditions, such as varying concentrations, temperatures, surface areas, pressures, or the presence-absence of a catalyst. Make sure to measure the reaction rates under controlled experimental conditions to obtain reliable data. 2. Analyze the data. Examine the data to identify patterns or trends in the reaction rates as the factors change. Look for correlations or consistent changes in the reaction rates with variations in the factors. 3. Draw conclusions. Based on the data analysis, draw conclusions about the effect of each factor on the rate of reaction. Determine whether the factor has a positive, negative, or negligible effect on the reaction rate. Consider the magnitude and direction of the observed changes in the reaction rates. 4. Apply the findings. Use the conclusions to predict the effect of the factors on the rate of reaction in other scenarios or conditions. Apply the knowledge gained from the data analysis to make predictions about the rate of reaction under different concentrations, temperatures, surface areas, pressures, or catalyst presence. 5. Validate predictions. Whenever possible, validate your predictions by conducting additional experiments under the predicted conditions. Compare the observed reaction rates with the predicted rates to confirm the accuracy of your predictions. It's important to note that predicting the effect of factors on rates of reaction relies on experimental data and observations. The specific impact of each factor can vary depending on the reaction and its individual characteristics. Therefore, it's essential to have sufficient data and to consider the specific context of the reaction. If you have specific data or examples related to factors affecting the rate of reaction, feel free to provide them, and I can assist you further in predicting their effects on the reaction rates. When studying rates of reaction, graphical representations of data can provide valuable insights and help in interpreting the experimental results. Here are some key points to consider when interpreting graphical representations of data obtained in studying rates of reaction. 1. Reaction progress versus time. A common type of graph used to study reaction rates is the reaction progress versus time graph. In this graph, the reaction progress is typically plotted on the y-axis, representing the extent of the reaction or the concentration of reactants products, while the time is plotted on the x-axis. The shape of the graph can provide information about the rate of reaction and its characteristics. 2. Reaction rate versus concentration. Another type of graph that can be used is the reaction rate versus concentration graph. This graph plots the reaction rate on the y-axis and the concentration of a reactant or multiple reactants on the x-axis. By varying the concentration of a reactant while keeping other factors constant, you can observe the effect of concentration on the rate of reaction. The graph can show how the rate changes with concentration, and it may reveal trends such as a linear relationship, exponential relationship, or a plateau at high concentrations. 3. Slope of the graph. The slope of a graph can provide information about the rate of reaction. In a reaction progress versus time graph, the slope at a specific point represents the instantaneous rate of reaction at that time. A steeper slope indicates a higher rate of reaction, while a shallower slope suggests a slower rate. In a reaction rate versus concentration graph, The slope may provide information about the reaction order, as it relates to the concentration dependence of the rate equation. 4. Reaction order. The reaction order can be determined by analyzing the graphical representation of data. If the reaction rate versus concentration graph shows a linear relationship with the concentration, the reaction is likely first order with respect to that reactant. If the graph shows a quadratic relationship, the reaction is likely second order, and so on. The reaction order determines how the rate of reaction changes with respect to changes in the concentration of reactants. 5. Catalyst effect. Graphical representations can also reveal the effect of catalysts on reaction rates. By comparing reaction progress versus time graphs for reactions with and without a catalyst, you can observe changes in the rate of reaction. If the graph for the catalyzed reaction shows a faster rate and reaches the same extent of reaction in less time, it indicates that the catalyst has increased the rate of reaction. 6. Activation energy. In some cases, graphical representations may provide insights into the activation energy of a reaction. The shape of the reaction progress versus time graph, particularly the steepness or flatness of the curve, can indicate the energy barrier required for the reaction to occur. Higher activation energy typically leads to slower reactions and flatter curves, while lower activation energy results in faster reactions and steeper curves. Remember to analyze the graphs in conjunction with the experimental conditions, such as temperature, concentrations, and other factors, to draw accurate conclusions. Graphical representations provide visual representations of the data and allow for a better understanding of the relationship between the rate of reaction and the variables being studied. If you have specific graphs or data that you would like to discuss or interpret, feel free to provide them, and I'll be happy to assist you further. Here are some key points related to the topic of energetics. 1. Energy. Energy is the capacity to do work or transfer heat. It exists in various forms, such as kinetic energy, energy of motion, potential energy, stored energy, thermal energy, heat energy, and chemical energy, energy stored in chemical bonds. 2. System and surroundings. In thermodynamics, a system refers to the specific portion of the universe under consideration. The surroundings include everything external to the system. The system and surroundings can exchange energy with each other. 3. Thermodynamic processes. Thermodynamic processes describe how a system changes its state in response to energy transfer. Common processes include heating or cooling, heat transfer, expansion or compression, work transfer, and chemical reactions. 4. Internal energy, U. Internal energy is the sum of the kinetic and potential energies of particles within a system. The change in internal energy, U, is equal to the heat transferred, Q, into or out of the system minus the work done, W, on or by the system, U equals Q, W. 5. Heat, Q. Heat is the transfer of thermal energy between a system and its surroundings. Positive heat, Q0, indicates heat absorbed by the system, while negative heat, Q0, indicates heat released by the system. 6. Work, W. Work is the transfer of energy due to the application of force through a distance. Positive work, W0, indicates work done on the system, while negative work, W0, indicates work done by the system. 7. Enthalpy, H. Enthalpy is a thermodynamic property that combines the internal energy, U, of a system and the product of its pressure, P, and volume, VH equals U plus PV. Enthalpy change, H, is the heat transferred, Q, at constant pressure, pH equals Q. 8. Endothermic and exothermic reactions. Endothermic reactions absorb heat from the surroundings. They have a positive H value. Exothermic reactions release heat to the surroundings. They have a negative H value. 9. Hess's law. Hess's law states that the overall enthalpy change of a reaction is independent of the reaction pathway and depends only on the initial and final states of the system. 10. Standard enthalpy change, H degree. Standard enthalpy change is the enthalpy change for a reaction that occurs under standard conditions, defined temperature, pressure, and concentration. It is often represented with the symbol h degree. Understanding energetics is crucial in many areas of science, including chemistry, physics, and engineering. It provides insights into the heat transfers, energy changes, and thermodynamic properties of systems. If you have any specific questions or need further information on energetics, feel free to ask. Here's the distinction between exothermic and endothermic reactions. 1. Exothermic reactions. Exothermic reactions are chemical reactions that release energy in the form of heat to the surroundings. During an exothermic reaction, the energy of the products is lower than the energy of the reactants. As a result, the excess energy is given off to the surroundings, often causing an increase in temperature. Common examples of exothermic reactions include combustion reactions, burning of fuels, and many neutralization reactions. 2. Endothermic reactions. Endothermic reactions are chemical reactions that absorb energy in the form of heat from the surroundings. During an endothermic reaction, the energy of the products is higher than the energy of the reactants. As a result, the reaction requires an input of energy to proceed, often causing a decrease in temperature of the surroundings. Common examples of endothermic reactions include the process of photosynthesis in plants and the reaction between ammonium nitrate and water. Key differences between exothermic and endothermic reactions include energy change. Exothermic reactions release energy, while endothermic reactions absorb energy. In exothermic reactions, the energy of the system decreases, and the energy is transferred to the surroundings. In endothermic reactions, the energy of the system increases as energy is absorbed from the surroundings. Temperature change. Exothermic reactions generally cause an increase in temperature in the surroundings due to the release of heat. Endothermic reactions often result in a decrease in temperature in the surroundings as they absorb heat. Reaction enthalpy, H. Exothermic reactions have a negative enthalpy change, H0, indicating that energy is released. Endothermic reactions have a positive enthalpy change, H0, indicating that energy is absorbed. Understanding the distinction between exothermic and endothermic reactions is important as it provides insights into the energy changes and heat transfers associated with chemical reactions. It also has practical applications in fields such as energy production, thermodynamics, and chemical engineering. If you have any further questions or need clarification, feel free to ask. Here are the energy profile diagrams illustrating endothermic and exothermic changes. 1. Exothermic reaction. In an exothermic reaction, the energy of the products is lower than the energy of the reactants, resulting in the release of energy. Here's an energy profile diagram for an exothermic reaction. Reactants. Backslash. Energy, backslash. 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 Potential energy. Progress of reaction. Products. In this diagram, the reactants start at a higher energy level, and as the reaction progresses, the energy decreases until it reaches the lower energy level of the products. The difference in energy between the reactants and the products represents the energy released to the surroundings as heat. 2. Endothermic reaction. In an endothermic reaction, the energy of the products is higher than the energy of the reactants, requiring an input of energy. Here's an energy profile diagram for an endothermic reaction. Reactants. Backslash. Energy, backslash. 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 Potential energy. Progress of reaction. Products. In this diagram, the reactants start at a lower energy level, and as the reaction progresses, the energy increases until it reaches the higher energy level of the products. The difference in energy between the reactants and the products represents the energy absorbed from the surroundings. The energy profile diagrams provide a visual representation of the energy changes that occur during a reaction. The vertical axis represents the potential energy, and the horizontal axis represents the progress of the reaction. It's important to note that the relative energy levels and shapes of the energy profile diagrams can vary depending on the specific reaction and the reaction mechanism. These diagrams are simplified representations used to illustrate the concept of endothermic and exothermic changes. If you have any further questions or need additional explanations, feel free to ask. To calculate energy changes from experiments or experimental data, you typically need to use the principles of calorimetry and specific heat capacity. Here's a general procedure. 1. Determine the mass and initial temperature of the substances involved in the experiment. For example, if you're studying the energy change of a reaction, you would measure the mass and initial temperature of the reactants. 2. Carry out the experiment and record the final temperature reached by the system. This could involve mixing substances, burning fuels, or any other process that involves energy changes. 3. Calculate the heat absorbed or released during the experiment using the formula Q equals mCT, where Q represents the heat absorbed or released, in joules, J. M is the mass of the substance, in grams, G. C is the specific heat capacity of the substance, in Jg times degree C. T is the change in temperature, final temperature minus initial temperature, in degree C. 4. If the experiment involves a chemical reaction, you can calculate the energy change per mole of reactant or product by dividing the heat change, Q, by the moles involved. This is done using the balanced chemical equation and the molar ratios of the reactants and products. It's important to note that the specific heat capacity, C, depends on the substance being studied and may vary for different materials. Therefore, you need to use the appropriate specific heat capacity value for the substance you are investigating. Specific heat capacity values for common substances can be found in reference tables or literature. Additionally, keep in mind that the calculations assume no heat loss to the surroundings. In practice, it can be challenging to completely prevent heat loss, so it's important to insulate the system as much as possible to minimize this effect. By following these steps and using appropriate measurements and data, you can calculate the energy changes associated with the experiment or reaction. If you have specific experimental data or additional questions, please provide them, and I'll be happy to assist you further.